Should we wait a couple of minutes? We're going. Yay. Okay, so we would like to welcome you all on our new edition of PyHEP 2021. We're very happy that there were so many registrations, so it seems like interest is very big. And we hope that you will have a lot of fun over this week. So you will learn a lot of new things, and please communicate with us. Yeah, just try to write in Slido questions and interact in Slack. There is a lot of interesting channels set up for you. So yeah, and I will start, probably I will not talk a lot. I will introduce Eduardo with a short announcement about workshop.
Hi everyone, can you see my slides then?
Yes, we can see your slides.
Yeah, so I really welcome again on behalf of all the organizing committee. So you see everybody here, we are a group of 6 enthusiasts organizing these things, some of us since a few years by now. Yeah, so it really is actually the 4th edition now, and the 2nd is a virtual event for obvious reasons. We had also an online event last year. But there are good and bad things, and it's very good. Something that I think should be stressed as it really allows us to be a truly global event with participants from all over the world. And you can see that from the top right distribution. This is taken by the way from your registrations. You can see that this time zone when we're speaking right now is pretty okay for the bulk of you, and that's precisely why we chose this time slot. So roughly afternoon for Geneva time, European time. As Oksana was saying, we had an impressive level of interest. Last year we had 1,000 people actually, and this time we went a little bit over 1,200. So thank you very much for that. I should also say that more or less 50% of the participants you see here are coming from the LHC. This is not that surprising. It just scales with the size of the collaborations. And well, the LHC collaborations overall, Atlas and CMS and so on, it's over 10,000 people, so really not surprising. What's really nice to see is that if you take that component out, and you look at distribution of non-LHC participants, you see that we still have a large number of communities attending this PyHEP workshop, and this is really fantastic, and we appreciate that enormously. In particular, you can see that okay, we have almost a quarter from university and research institutes participating, and we have a big component, a big participation this year for the first time, by the way, from the neutrino community. All right, so this I'm not going to read it all for you. This is actually taken from the very first workshop in 2018, but I would say I would like to stress that this has not changed. Our goals are pretty much the same. In particular, the only thing I would really want to emphasize is that we try to bring together the community, be developers, users, or enthusiasts, so to share the experiences, also discuss the trends, new packages, and so on. So in the end, it's a win-win situation for everybody, whether you are simply a user, so to speak, or actually a developer. So you have something that is by the community, for the community. So this really is very important. The other point that is super important, as I have seen as well from the way we organize it, is that we allocate a fair amount of time for lively discussions. So do profit from the fact that this is not a conference. You really have a fair amount of time for discussions, even live, right? Typical presentations are 20 plus 10 minutes. So enjoy it. And for the rest, of course, you have the various topical Slack channels for any discussion offline. Right, so talking about Slido, at the end of the presentations, so during the Q&A sessions, we use Slido, so you must have seen this from the emails, but just remind you, here's an active link as well. You can start posting your things, whether you want to do it anonymously or with the name, up to you really. The nice thing here is that it allows you to crowdsource the questions. So you have the possibility either you post a question yourself, or if you see a question that was posted and which you like particularly that you can vote it. And then in the end, what is good is that we have a prioritized set of questions that we can go through in that Q&A session, and all the rest can be then discussed offline if time did not permit right, at your leisure. So this is, I think, again, a nice way, and this has worked extremely well. And last year, by the way, and this is how it looks like in blue. Right, so this is again how the feelings. So you can see, like for example, Ben last year can have a question, and then people can go and upvote or downvote if they think this is not so relevant. They would like to see something else. That's perfectly fine. It's a democracy. So, and the other thing again, you can put your name or not. Depends as you wish. Again, if you put your name, then we will address your name. If not, then we just address the questions. That's just as fine. As I mentioned already several times, what we cannot answer and discuss during the Q&A session is posted on Slack, and everybody is welcome to contribute and continue questioning the speaker in particular, and anybody interested in those discussions. So this is how it looks like. Just try and do the replying thread, so you can get all different threads together, and it makes it a little bit easier, especially if you have a large number of them being posted at the same time at the end of the presentations. Another point is you've seen that we try to encourage quite a bit the use of notebooks for what we call notebook presentations, and also to have a more smooth, enhanced experience. We use Binder for that, and we even had an example GitHub repository where you could find how to set things up if you're not too familiar with it. And here we really wanted to say a big thank you for the Binder team in allocating us extra resources during the workshop. So this is something that we have done for the first time last year. As you can imagine, if you have 2-3 people launching a notebook at the same time, that's fine. But if you have 300 people launching the same repository at the same time, the experience might not be so smooth. And the fact that they allocate these resources in due time for the relevant repositories is something that makes the life and the experience really smooth and nice for everybody. So just really appreciate it. By all means, if you want to engage more with them, you have a couple links there, mybinder.org or the discourse for finding any discussions from the Binder team. Another big thank you is for our sponsors. So you may or may not know that we have been capturing the recordings of the workshops. So, and this is thanks to the kind sponsorship of these institutions, and we wanted to thank them explicitly. So at the end, I just have 2 things to say. First of all, enjoy very much the week. I hope you will enjoy it as much as we have been enjoying in the last few incantations. And because we do like to engage with communities, so you'll probably hear this word very often during the week. We have an announcement from a colleague that is further engaging with the SciPy community. In particular, he's organizing a Birds of a Feather session on the topic of Python in aerospace and astronomy. So again, if you feel concerned about that, you can either go and discuss that and see with him directly on the GitHub channel, or email him privately. So this all here. The slides are posted on Indico, so you can always go back to them if you have missed anything. That's pretty much what I wanted to say. It was just an intro, not a boring half an hour discourse. So thank you very much, and again, have a good week.
Thanks a lot. Perfectly in time, Eduardo. So, yeah. So we are moving now to our first tutorial, which will be done by Henry Frederick Schreiner. Henry, I just made you co-host. Yeah, I see you could you share slides? Could you share screen?
Yes, I will in just a moment. There we go.
So yeah, for everybody is basically short course in intermediate Python. And then after, I think tomorrow we will have a second part. So please enjoy.
Okay, so we'll be doing Level Up Your Python. There are links to the binder, which will take you into this Jupyter Notebook environment that I'm using, as well as a link to a web version of this, where this gets rendered out into slides using JupyterBook, and the repository itself. You'll find all those links in the Indico page. If somebody wants to paste one into the chat, that might work as well. Okay, so we will not be covering all of the material you'll see in there. We'll cover a subset of it that will be roughly, it should roughly look like what you see in the README. So we'll cover memory model classes, debugging, profiling, and possibly static typing today, depending slightly on how much time we have. If we have an hour and a half. And then we'll cover some more things tomorrow. And this is somewhat tied to a talk that you'll see on the fourth day that I'll be giving on packaging. And you'll see some of that material is related to the material in here. Okay. So this is really targeted at intermediate Python. So this is not a beginner course. You'll see a lot of beginner courses. This is one that's actually targeted for someone who's a bit further along and wants to try to move into using Python better, but already knows some Python. So at this point, hopefully you already know basic Python syntax. You know how to write functions and classes. I'm slowly building up some introductory material to classes there, because sometimes people come in without much knowledge of classes. And NumPy, and of course you should be familiar with Git at this point, hopefully. If you're not, there still will be a lot of interesting information here that you can come back to later. And if you're a bit beyond this, hopefully you'll still find a few things interesting, or find a few pieces that are a good review. I will skip about the author part except for this link. So this is the link to my blog, and I have basically the same set of links there, including a link to this material. So you can get to most of the material that I provide from that, from the top of that link. So I need to say just a little bit about expectations. We only have about an hour here, and I don't know what you know, and we really don't have time to just sit here and focus on anything in depth. So we're going to move very, very quickly, and we're going to cover a lot of material. You're not expected to be able to master everything that you see, but you are expected to pick up ideas. So if you know what is possible, then you'll know where to look for that. And you'll also have material that you can refer back to later. So we're intending to go fast, and that's fine. And I would like to mention a little theory here, and that is that programming is really all about organization. And this has a lot of consequences throughout the things that you'll be seeing today. And one of the main consequences of that is that new features in general remove functionality from the user. They don't add something, they remove something. And that's good, that's what we want. So let's do a quick example. If you're a little bit further in Python, you can substitute pretty much any feature in here. In my mind, I would substitute context managers, but we're going to look at goto. So goto loops are, gotos are actually not in Python, though you can actually, that was actually added as a proof of concept library, but people generally try to avoid them. But a goto is actually much more powerful than a for loop or a while loop or a function. You can write any for loop, any while loop, any do while loop, any function as a goto statement. They're a more powerful thing than the for loop feature. So why is the for loop the better thing? Well, this is an example of a little goto where I set up I equals 0, I add a label, then I print something out, I add 1 to I, and then if it's I is less than some value, I just go to the start label. So I then cycle around. Compare that to the matching for loop. And these are things that we can run. With the for loop, I'm much more restricted. I must write a loop that loops over something. However, as when you're reading this or you're thinking about this, there's much less thought that has to go into this. Once you learn what a for loop does, now you immediately know exactly what this is supposed to do. It doesn't do anything weird because you know exactly what for loops do. Here you have to study every single line and understand what this is doing, and eventually maybe recognize a pattern. And a larger example, of course, that's much harder to pick out. Even a fairly new programmer will say, "Well, this is 0 to 9," whereas here you have to check and see if I is done. Check and see if I is incremented. You have to look and see a lot. See a lot of things. And that's true with all of these features. Yes, you might be able to build whatever this is out of basic constructs. You can build any program out of very, very, very basic constructs. The idea with programming is that if you use the more advanced features, then someone just has to learn one thing, and that works across all Python programs. And then they can just recognize the patterns. You work at higher levels. Humans like higher level concepts. Okay. We will be using notebooks today. We'll be hopefully you'll be able to run these on Binder. There'll be things that you can run. So try running things along with me. I highly recommend that. And then quick note on Python version, everything we'll be doing will be sort of targeting 3.7 and newer, which is what NumPy is using, and a lot of other scientific packages. But we'll be running 3.9, and once in a while we'll use something from 3.8 when we're running. Okay. So let's start with the Python object model. So in Python, everything is an object. And technically in CPython, which is what we'll be talking about mostly today, this is represented by a PyObject star, but other implementations are similar because they're implementing the same language, so the structure is the same. And then an object is just an instance or of a type or a class. Okay. There are some special optimizations and things to the built-in classes so that it's not infinitely recursive, but as far as the language is concerned, this is true. As far as the CPython implementation or any other implementation, there are some tricks that are built in. So for example, let's just define a number here. So v equals 4. And even a simple integer has methods. So if you call bit length, that will tell you how many bits are required to store this number. Python's actually using far more bits than that, but that's the technical amount of bits required to store the number. And let's try defining a function. Function is called f. Now I will be using type hints pretty much anywhere I can. And we will hopefully get a chance to talk a little bit about what they mean later. But right now, these are just aids to help you understand that I'm expecting an integer in and I'm producing an integer out. Okay, and I can call that. Okay, this is also an assignment, just like we said, f equals 4. This is an assignment. This is creating a new function and assigning it to f. There's a few things special about this assignment. One of them is that Python actually knows the name. So if you were to ask f dunder name, which is this here, it actually knows that it was assigned the name f because it's in the special def assignment instead of a regular equal sign. With the regular equal sign, there's no way for this object to know that it's been assigned here because there's all sorts of different things that could be over here. All right, so I can swap these things. I can say f and v are equals to v and f. Anyone have any idea what f or what is v now and f, and how about the name? I've got a few people just type that into the chat. Might be a good way just to think about it for a second before we move on.
Not the Zoom chat, into Slido.
You probably should open up the Slido window.
And as a reminder, everybody joining by YouTube can also open Slido.
So Slido is for polls. Does it also have a place just to answer a question?
Q&A. On the top bar next to the poll is Q&A. There.
Okay, perfect. Somebody wrote that out. Okay, they said that v and f has been switched. That is correct. This is assigning, so this is a tuple on the left, tuple on the right, and this is assigning v to f and f to v. So what is the name? So we said f is now v, so I have to type v name. So what is the name of that? All right, someone said F. It is. So in this special assignment statement, it knows the name and it sets the name as part of this, as part of the structure it's setting up here. But that's just attached to this Python object. And if we change what labels we want to call it, the name is still F. This V is still the function F. Okay. So we can pass functions around. We can put functions in objects. They're just objects like anything else. They just happen to have a call method. So you can call them. Other things might be callable too. So let's look at inspecting things a bit. There's a variety of different ways to inspect objects. I have a list of some of them here. One of the first things that you could probably use is help. So if you define a function here, so here's a very similar function, but this one is, I'm intending to take floats. And if I call help, you'll see that I actually get this string, the very first string that you put in a function here, and I get the signature. In a Jupyter notebook, you're running the IPython kernel, so you can actually write F question mark, and that will also give you help. So it'll give you the signature, the doc string, the file that it's stored in, which is a temporary file because this is just in a notebook cell, and then the type of the object. Another thing that's built into Python is you can call dir. Dir will give you most of the attributes on that object. It does not have to give you all. People can control what dir does, but usually this is all of the things that you can call. And you'll see functions really just have a bunch of these magic methods, under methods. Okay. You can also use the inspect library. This is one that's built into Python. There are several useful things in here. One of them is get source file and get source. So the source file will return that thing you just saw, that temporary file that this is put in, and source will give you the actual source of the function. So there's the exact source. This is really useful if you're working with a library and you want to see what it does. Now, just a quick word of warning there. This does not always work. Python does not store the source. It does not store the AST either. It only stores bytecode. And often when you are running Python, it's not even loading that at all. It's loading the bytecode only. It creates these .pyc files. A little bit more hidden in Python 3, but they're there. And it's loading that. But usually it has a link back to the source, but that's not guaranteed. So if you're writing a library, don't depend on this for your library. But if you're in a live session, perfectly fine to use this, and most of the time it will work, but not always. So there is a library called Rich, and Rich is a library for extremely advanced terminal formatting. It's really, really nice library to use, and it has an inspect function. It has all sorts of things, but inspect is one of the things it does. So if I call rich.inspect, then it will print this out in a terminal, and it works in Notebook too, of course. And it gives you this really nice, colorful display. And there's all sorts of options. So try, let's just do inspect a number here real quick, so you can see something that it does different things for different objects. Try adding a few options on your own. So if you want to see what options there are, there's one more way to inspect things I've not mentioned. If you're in a notebook, you can press Shift Tab. Shift Tab will give you the help in a little pop-up window in the notebook. So try adding a few of these things and just see how this changes. I'm going to try adding. All is probably the most useful one to add. That way you'll just dump everything, but let's try, I'll just try all. So now it's dumping.
Henry, there's a question on Slido. I don't know if you've seen it, if you wanted to be aware.
I'm going to pull this out, and that way I can see Slido while I'm presenting. All right, so the question is, isn't it generally bad to define input and output types in Python functions? So I assume you're referring to this. And so what this, we'll talk about it a bit later, but these are type hints. So they are telling you that that I'm expecting a float and I'm expect to return a float. Okay, so this is, you could avoid this, but you want to add this. This wasn't possible before Python 3. In Python 2, you could add it as a little comment, but you couldn't add this directly. So people avoid it because in the past, because they were trying to keep Python 2 compatibility. And you have to realize that these are not guarantees. In fact, at runtime, they don't do anything. In fact, if you add from future import annotations, they literally just turn into a string. Python doesn't even evaluate them anymore, which is really nice because they're a type hint. And well, there's a way to use them, and they're extremely powerful, and they can really make both your code and anybody using your code much more robust. But they don't actually do anything. I could pass, so I can pass f string in there, and I will get an error here because that doesn't make sense for the star operator, but I will not get any errors here. But there's a way to do that, and we will discuss that at the end. Okay. All right, so now we see all of the different things that get defined for a function. So you'll see that functions have a bunch of attributes, and that's actually what they are. So if you're trying to learn Python, knowing about inspect, especially rich.inspect, can be extremely useful. Just so that we don't have a tremendously long thing, I'm just going to reduce that. Okay. And someone has a question about F and V, about those switching. We'll talk about assignments a bit more. So I think we can move on, and then you'll see a little bit more in assignments. Okay, and again, you see switch.inspect. It gives you the non-dunder methods right away. Okay. So let's talk for a minute about mutability. So this is something that's a bit unusual in Python. There's actually, in Python, there's no concept of pass by value. Everything is always pass by reference. Whenever you assign something or take something as a method order, you always get a reference to it. The thing is that a lot of the built-in types in Python are immutable. They can't be changed. And because of that, it feels like you're passing them by value. So let's do a little example. So we'll set x equal to 3. We will then assign x to y. And then we'll do an x plus equals 1. So this looks like we should be trying to modify x. So if we do this, what is y? So to see the answer to this, just add an f to the string, and you'll see the answer. I don't have that there, so that if you're reading the value, or if you're reading the web version of this, you won't see the answer immediately. Someone's already answered it, so I can run that. So y is 3. So that looks like we've created a new copy here, but that's not what happened. At this point, x and y are the same. X is y. They are the same. So at this point down here, they are no longer the same. So the place where x got changed is actually not here, it's here. The plus equals, we'll try to assign it in place, but for some things like built-in types, it's actually exactly the same thing as writing x plus 1. So that changes, that gives you a new object x. So that's basically what this turns into. But now, let's try this with something that's mutable. Okay, so a list is mutable. So we have a list with a value 3. We assign that to y, and then we change an item in x. So what is y here? Just try running that on your own. And I'm going to go ahead and run that here. Y is now the list with 4 in it. So that the x plus equals did mutate as it was expected, and the contents changed. So if you have a mutable object here, then you can tell that assignments actually keep them the same. So if I say x is y here, that's true. If you want, you can look at the memory address. Somebody's asking about that on Slido. The memory address of x is equal to the memory address of y, which is what the is does. Is just checks to see if the memory addresses are the same. Okay, so these are both pointing at the same PyObject star in the background, and that PyObject star actually changed. Its contents changed. Okay, just a quick aside on why this works. We're going to go ahead and skip that, but you can review this on your own. But there's a little experiment that demonstrates how to use the mock library and then to put in an object that we can monitor. And examples of a few pieces of syntax that are also kind of special. It turns out this assignment is actually a little bit special because you're actually applying it to y. This operation gets applied to y and not the contents of y. Okay. Someone asked a good question. What if you don't want to change that? If you don't want to change it, you can manually copy it. There's a copy library, copy.copy, along with copy.decopy. So you can make copies, but they don't happen by default. And someone else asked if there's a way to force immutability. Mutability, somewhat, yes. That tends to be kind of special for the built-in types, but there are ways to create objects that are not easy to change. You can't create one that's impossible to change in pure Python, but you can disable you can make it act a lot like this. Okay, and also there's just a few types of assignments in Python. And I should have mentioned that this actually is allowed to be a tuple. But this could be a tuple, this can be a single value, this can be a x with a get item, and which becomes a set item, and a attribute, which becomes a set attribute. So all these other expressions are not valid assignments. You can't assign any other cases than these. The thing on the left must be one of these simple things, or reduced to one of these simple things. So x could be fancy, but then this thing's got to be at the end. So you can't assign to a function call. You can't assign to a expression. You can't assign inside parentheses and that sort of thing. In Python 3.8, they added a way to avoid this, to do these sorts of things with what's called the walrus operator, because it looks like a walrus sitting on its side. But that's the only way you can do these sorts of assignments. Another thing that comes up in Python is scope. So Python really does not have much scope, a lot less than some languages like C and C++. For example, and it's actually useful due to the way that it's designed. So for example, I say if equals true. In C++, this would, or C or C++, this would create scope. So if I said x equals 3, then I leave the if statement, the scope is now ended, and anything I created in that scope gets thrown away. In Python, that doesn't happen. The if statement does not make scope. So I assign something inside the if statement, and there it is. I can still see it after. And it's really useful because in Python, up until fairly recently, there was no way to define things. You couldn't say in C, you could say, well, there's going to be an x up here, and then I assigned to it inside here. But now it was created outside the scope, so it's okay. You can't do that in Python. This is not valid before you've assigned it. Now there is a way to do that now through type hinting, but type hints do not change the runtime. So I could say x:\int. There I've defined x, but again, regular Python's not going to do anything with this assignment, and plus it didn't exist when they were developing the if statement. So it doesn't create scope. So there are only a few places where scope exists. Scope occurs inside functions. So a function creates scope, a class creates scope, and a module, a file, something.py, those create scope. Those are really just about the only places that make scope in the language. Because scope is so rare, it can actually come and bite you once in a while because you're not thinking about it. So for example, and also just to mention, this is generally a bad idea because if x had been false, then x would not have been defined. So you have to be very careful to define it, both x in the if statement and an else statement, or otherwise this is probably a bad idea. But just to let you know, since I'm just showing you that. Okay, so I create, say, x=1, and then inside of f, inside of this function that I'm defining, I can actually access x. Okay, so I can access x inside f, and I can access x later because it's obviously not defined in f. If I had, just to prove that this does have scope, I could define it in here. I've actually already defined it, so let me pick something I haven't defined yet. Definitely haven't defined that yet. That will fail because y got created inside of f. This does have scope, so it's not visible later. Okay. Just to show you that does actually create scope. Okay, so here's one of the things that can surprise you. We don't have to return that. And that is if, for example, you do an assignment. So x=1 up here. I'm assigning x=2 here. Just think about that for a second. What do you think will get printed out? This printed 1, 1. What do you think will get printed here? So think about that just for a second. And we'll run it. Okay. So this printed x=2. Right? So this printed out 2. But out here we printed out 1. Why? We just assigned x=2 up here. Yes. All right, somebody responded because print x takes the scope, whereas 1 takes the scope outside the function. That's correct. This x is in globals. It's in this, it's right here. Inside here, we created a new scope. We assigned in it. That created a brand new x. So this x is not the same as the global x. What happens if we switch the order? Somebody try that. Switch the order, do that. What will that, think about that for a second. What will that print? And then try it. So somebody's mentioned global versus local. This is all really a scoping thing. The things that are in the most outside scope are called global. And you can actually access them, as you'll see in a second, using the keyword global. But they're really just different scopes. So if you have function inside of a function, you now have 3 levels of scope. If you have, and modules, what is global for in a module, something you call global may actually be or that's what you think of sort of as global or sort of module level scope is actually only local to that module. Okay. Things you type in the interpreter are global. Okay. So if you run this, it's actually it actually fails. It sees that it's going to have X in the scope, and then you're trying to access it before you've assigned it. So it's actually a failure. It didn't print 1, as you might think. it's actually a unbound local error, because this is in the locals. There's a local variable named X, but you're trying to access it before you've defined it. Okay, if you did want, if for some reason you really did want this behavior, then you'd have to use the global keyword. Okay, so now there's only one X. This is not making a new X. And now this really does print 1, 2, that's, you know, some people expected a while back. So because now we're referring to the same thing. So here's the rules. If you access a variable, that grabs the first variable it finds going up in scope. So the local X, if there's a local X, the non-local X, the one that's above that, then the one above that, et cetera, until you hit the global scope. And then if there's nothing in the global scope, you get an error that you're trying to access an undefined variable. Setting a variable always uses the local scope. So whenever you assign a variable, whenever you say X equals 2, that creates a value X in the local scope if 1 doesn't exist. Okay, so that's just how Python works. There's a couple of ways to get a bit more control over that. For example, this global keyword. And there's also a non-local keyword, which will go up 1, but not to the global. It's actually an error if it's a global. And so that's how you could get this behavior. If you'd like a practical rule, always pass variables in and out explicitly, especially out. And be very careful if you're ever using anything that's not global in a function. It is not a horrible idea to use it. There are a few special cases where you can access stuff, but in general, you should not be doing this at all. You should make X a parameter. You should say X, something like that, and then you should pass things in and out explicitly. It is really hard to refactor code or to even understand and read code that's secretly grabbing scope, secretly grabbing variables from the outer scope. Sometimes you need to because it's handy or useful, but generally, even just using it is not a great idea. Certainly, actually assigning to it is an even worse idea. So most of the time, you should not see this. If you do have a global variable that you do access, it's a good idea to make it all caps and then never change it. So global read-only variables by convention tend to have all caps. Okay. And somebody asked a very good question. So global inside the function will make X global only when you're inside the function. Is that correct? So that's a good point, because this, what all this really does, it's like a define, and it says, when I refer to X, I'm going to refer to the global X. There's a variable in the global scope called X. If you assign, and there isn't a variable in the global scope called X, it will create one. And if you're using it, you really don't need the word global, because if you only use it, because you can always access something in an upper scope, since that's how the accessing works. But this only affects the current local scope, whatever scope you're in. That's changing it just for this. So once you leave the function, this is gone. Okay. So memory in the garbage collector. Python is what's called a garbage collected language. That means that every object, every PyObject star is actually holding a ref count inside, saying this is the number of times I'm referred to. So it sort of tells you how many different ways you can access this object. Usually in normal Python, that's roughly once per line, but that can be changed. And it is a little bit different in PyPy. So let's take a look at a piece of code. Notice I'm doing something a little bit unusual here. There's one character here that you don't see me use very often. But I'm going to create a little class. That class is going to have a destructor. This thing will run when the object gets deleted. I'm going to ask the garbage collector library, if it's tracking this object. Yes, this is a tracked object. in the garbage collector. I'm going to count get the ref count. That's 2, because this is obviously one of them. And then the garbage collector is holding it. So this ref count will never show a number less than 2. Because I've got it, and then the ref count function's got it. Okay, and then if I delete the object, you'll see that on this line, the object got deleted. All right, so let's try a very tiny variation. What was the character that was new here that I've not been using? I added a single character. Does anybody notice what that character is that I have not used before? Yes, somebody has put semicolon. So let's try it without the semicolon. The reason I put the semicolon is I wanted to make sure that there's no chance this got displayed. Sometimes I have display all assign the final thing on every the final thing on every cell turned on. I don't think I have it turned on right now, but sometimes I do. Let me check. So yeah, I don't have it turned on. So I'm going to have to manually display that. Okay. So I was making sure it did not display. There is a way in Jupyter Notebooks to have it always print out whatever you assign. Okay. So now I'm going to delete the object. There was no boom here. I deleted it. I said del. That should have run saying the word del should run delete, right? Well, no. This only gets run if that object gets deleted everywhere and the garbage collector collects it. This didn't. My del only deleted my reference to it. There's another one. And that reference, if you were just running these through, is number 24. I can actually see it's 42 for me. There we go. There it is. So IPython is actually keeping every output you see, it's actually keeping a reference to that. And so it's still accessible. Since it's still accessible somewhere, it's not deleted. And I've actually tried for a little while to get rid of all the references to it, but once it gets in here, it's just, I gave up and I couldn't find all the references and delete them. It's not collectible. There's actually there's something even worse about dels. At the end, everything starts getting deleted. Everything, including modules. So if your del uses, say, let's say I did like sys dot something. Don't do that in your destructor, please. But let's say if I did that, this might not be valid because sys might have already been deleted at this point, because Python starts deleting everything. In later versions of Python, I think they give you a little bit more, there's a little bit more of a guarantee about orders of things, but certainly third-party modules could easily be gone. Other modules in your library could easily be gone. I think system modules may wait to delete those until the end. But of course, if this gets called as part of, say, a callback or something in a system module, then you really can't use much of anything inside a destructor. So there's actually a much better thing than a destructor. If you're used to C++ and the resource initialization is acquisition concept, then there's a tool in Python that mimics that, and that's called a context manager, and we'll cover that tomorrow. So we'll just sort of jump over this pretty quickly. Just point out a couple things from importing. When you import things, and then I'll answer the questions on Slido. So there's several different ways to write an import statement. If you are importing a module, there's a nice benefit to this in that B is guaranteed to be a package or a module, a file sitting on your drive. This one, B could be a module, a package, or an object that was inside of one of those files. And because of that, this is rather nice if you have modules or packages. And this should really be dedicated mostly to importing objects, hopefully things that say are a class and have a really obvious capital letter at the beginning of their name, because it's a convention. And therefore the reader can immediately realize that this is a general object and not a module or a package object. I'm sort of differentiating between a module and a package and an object here. Obviously, everything is an object, so packages and modules are objects, but they are a module object. So that's why I'm sort of do that. And also, if you say import A, and then you call a.b, is that valid? And that's only true if A is an object inside. B is an object inside A. If you write import B inside the file that's A, then this will be valid because it's an object sitting inside the module. But it's only true because you did that. Otherwise, you have to manually import it. And the other thing to point out is that whenever you have something like this, all of the init.pys run. So A's init.py runs before it gets to B, and then B's init.py runs if it's a package. Okay, a little mention about circular imports there. I'll let you read that on your own, but there is a benefit to importing packages instead of objects if you're under risk of doing circular imports. And then I have a little discussion about relative imports and where imports come from on your path. I'll let you read that on your own. The one thing I'll show you here is that if I have say import sys or some module, I can now look at what the file is by doing sys.file. Oh wait. Except maybe the system module doesn't have that. Let me try one that's actually, I know exists. Oh, I don't have that in this one. What's one that I do install? Rich. There we go. Sys didn't have one, I guess, for some reason. I don't know. Totally sure why, because it does exist. There is a sys.py. But for certainly third-party libraries, this is a way you can see exactly where it is and look inside it and stuff. Okay, let's answer a couple questions. If someone asked if it's bad practice with class methods to access variables using self.variable then passing explicitly, that's sort of what classes are for. That's the one, and that is sort of an alternative to having a function that grabs a bunch of things from the surrounding scope, is to make a class, and then you can use self.whatever inside the class. So it's perfectly fine to call self.values. There are some rules, and we're just about to get into classes for classes. And for action at a distance, what I mean is if you have you call something. So when I mentioned action at a distance here, if you call something and then you have some other function that you want to run later, and that should always run. So if you open something and you want to close it, or if you start something and it has some sort of finish that it always wants to run. So that's what I meant by action at a different distance. There's a structure in Python called a context manager, and we'll cover that tomorrow. In C++, you would often use objects to do this because you're guaranteed when they get destructed. So therefore, you might have locks and various things like that through class objects. And you create one, and then you just let it get destroyed at the end of your scope. And that's how you run a function later. You guarantee a function will always run later by doing that in the destructor. That's not a valid structure in Python. You can do a little bit with the del. You can try to make sure things get cleaned up, but you just about can't guarantee it will run. And there is something that does that in Python. Okay, and someone asked if there's a command to show all the attributes in the module. Great question, because we've already shown it. That should show you everything that's in the module. Now, the user has some control over this. You can actually customize what dir of an object does, but that's how you see everything usually. And if you do customize it, hopefully you're customizing it for a good reason. You're, say, removing something you don't want somebody to use. Okay. And there's some discussion, someone was asking about importing stuff. There's some discussion on how you do that. You modify the sys.path if you have to. Usually, though, you use the packaging stuff we'll talk about if we have a chance. All right, let's go ahead and move on. So let's go into object-oriented programming. Now, hopefully you know a little bit about classes here. If not, go look them up and learn about them, but we'll cover some of the features of a class. So hopefully at this point, writing a class is fairly natural. So here's a little function that I wrote. And I could write a class to do exactly the same thing. So I create a class, I give it a call. So these are the variety of special methods that have these double underscore names. And whenever you use a class, you create an instance of it. So I call the class, parentheses, to get an instance. And now this instance works exactly like the function f. So this is Python 3.8 syntax, but since we're just using it for printouts, it should be fine. And there we do it, and it behaves exactly like that. But classes have a lot of extra features, including the fact that you can assign attributes and then use those. So it's a great way to pass around these values instead of just capturing them outside with some scope, because it's explicit. You know exactly what a class is carrying, and you can create multiple classes, so they're not global. By that, I mean the instances are not global. Okay, we're not going to go over the advanced section here. I'm just going to go to the table of contents. We're just going to jump over this, but there's a variety of different things here that you're free to look into if you're interested in things like some of the advanced details of how classes work and accessors and special methods and things like that. We're just going to jump directly to uses for classes. Okay. So these are a few uses. Let's look at one here. So one common use for a class is to store data and functions together. So let's say you have a detector module and you have specific information about which detector module you're in. And you also have some function that only works on detector modules. You can put that inside a class. In my example here, I have a vector. So vectors store an X and a Y. And then they have a magnitude. So I can create a vector with X and Y. And then I can call a magnitude on that. And that computes the magnitude of the vector. So you can store these things, the data here and the methods together, because this self is expected to always be a vector. And I'll mention a little bit more about that maybe. So this is actually a lot of boilerplate. So I didn't write a very good class here because, for example, let me just show you what the repr looks like. That's not very helpful. I would really like to see what X and Y are inside the repr. I would like for this to have a few features. So I have to actually go and add a bunch, well, several more, 3 or 4 more of these dunder methods to make it behave nicely. And I also had to repeat myself several times here with X. I had to write X 3 times here, here, and here. And that might discourage me from writing a bunch of classes for things that I could use them for. So there are tools for that. Adders is a third-party library that's really, really nice. And it was actually so nice that they built it into Python in Python 3.7 and newer. And there's actually a backport of this exact thing in Python 3.6 called data classes. So often if you're sort of thinking this is ugly and especially if you're tempted to write something like this, X equals something, or write X up here, which is wrong, you can actually do it now with data classes. So with the data classes, all you have to do is stick this thing in front. We'll talk about decorators tomorrow. But you just stick this thing in front of the class. Now you can just write these things at the class level. X is float, Y is float, and this data class will go and generate everything for you. It will read these things in, and it will generate them for you. So now I have exactly the same thing I had before, but if I look at V, I get a pretty thing here, there's actually a bunch of different things it generates for you. And this is a much nicer and more natural thing. And I wrote X and Y exactly once, not 3 times. And you can actually write a lot of classes this way. It's a different way of writing, but it's really quite nice once you get used to it, especially for these quick classes that store data and values together, data and functions together. Functors, we talked about this a bit before when we were talking about this global scope. This is one use case for a global scope. Let's say if you want to create a function that increments every time. And so I write incr and I get 1, and I do it again and I get 2. So this just keeps returning a value that's incrementing every time. This seems like kind of a useful thing, but again, I told you this is a really bad idea to use the outside scope. It's much better to pass things in which case this increment function is pretty ugly. But this thing uses this global. I can't make 2 incrementers for 1. This is kind of ugly to read because I have to look at the definition to understand exactly what's necessary. If I go delete this, then it breaks. It's not obvious that it's using it unless I look inside the definition, and looking inside definitions is bad. So here is a different version that uses a class. This time I store the data here. I could write this as a data class too. Fun exercise for yourself might be to try writing this as a data class instead of as a regular class. But I have a single value incr that gets passed in, and then I do a call. So now I'm using self.incr, and that's fine to use. As a class, I'm expected to have access to the stuff in the class. And technically it is explicitly passed in right there. And then I return that. So now I get the same behavior, but I can make as many incrementers as I want, and I'm not using globals anywhere. So usually there's ways to get around globals. This is one of them, and it's a use case for a class that your state is being stored, is being bundled up and stored inside this explicit object. Okay, someone had a quick question on data classes I want to answer. Can you add a init to a data class? Yes, you can override the init and just ignore the init that it provided, but that kind of wastes a good portion of the data class because you want it to make your init for you. There's actually a special method for data classes that runs after the init, but before the object is created. And I forgot the exact name. It's like init data class or something. And if you define that one, you can actually modify what happens, change X and Y, whatever, but you still get the benefit of it generating the init for you. But yes, absolutely. You can override the init. You can tell it not to make an init. And you can override a special method that is run. The init function in the data class runs the special function at the end. So yes. Another thing is for modularity. So this is a pattern that you'll see. This is one that Geant is pretty much built on. But you'll see this pattern a fair amount. And that's where, say you have a class and say it has several methods here, part 1, part 2, part 3, and then it runs them. So for Geant, these are various physics processes and things. And then the way that you could, so this sort of separates this out into several functions that then get run. Now, the benefit of doing it this way is you can use inheritance. You can say, well, I'm going to make a new class that inherits from this one. It has all of the same methods, but then I'm going to replace part 2 with a different one. So if I do that, and now I was able to replace part of the code without having to go, I didn't have to re-implement this thing. So this might be hard to do. This might be a complicated thing, or might be tons of stuff, and I might not know what all runs in here. But now I don't need to. All I need to do is know that I have this hook. I can implement a part 2, and if I do it, I get that. Keep in mind, this may not always be the best design model. Think about it before you do it. But this is a design model. So I'll point out at the end, I'll point out a link that discusses sort of some of the concepts. So there may be other ways to do this, but classes are one way. Another example of a use case for a class would be for a domain-specific language. Technically, this is an EDSL or embedded domain-specific language. For example, I can create a path object that behaves exactly like a string. It inherits from string, except it also supports division. And for the division, and this is a pattern you'll see fairly often, I'll call self.class. I'll always try to refer to a class as self.__or class and not using the word path, because this may get inherited and self.class might be the inherited thing. So you'll be a lot friendlier if you always use self.class. So that's a common pattern. Usually try never to name the class inside. Okay, so if I do that, I can now create something that just builds a path by division. There's actually a library in Python 3 called pathlib that has exactly these things. That's a very, very natural way to work with paths because it supports things like this. Also, just a quick example of a mix-in. A mix-in is a specific design pattern that lets you, so one of the issues with this is it's not modular. You can't, if you wanted to apply this to several different classes, you can't. It's one of the issues with subclassing because it's a linear chain. Mix-ins lets you do this without doing that linear thing. So I could actually have created this as a mix-in, and then I could have mixed it in to string here. So this creates a mix-in class that only has this. I left the static types off here because it's a little tricky to static type, though there is a way to do it. And then mix it into a path. And now I have exactly the same thing, but I could have mixed this thing into something else. So it's reusable. So you have to be very careful whenever you see multiple inheritance here. You have to follow very specific rules. Like you should avoid init. This should not, mix-ins should never have an init, stuff like that. You should never have your own data members. But if you follow those rules, it can be very useful. NumPy uses this. There's a lot of our libraries use this. And there's some other things I didn't talk about. Protocols we'll see later if we make it to the static typing section. That kind of depends on if we have a following speaker or if we don't. And then there's some design considerations. So you should try to, and these are general design considerations, but they're extremely important in object-oriented design because it's really easy. And what some people have done in object-oriented design has gotten a bad rap in some places because it's not a replacement for organization. Programming is organization, and it should help you organize your code. It should not be something you just apply like a shotgun to everything. You will easily create a spaghetti mess out of your code that's impossible to refactor, understand, or read if you misuse it. So these are some tips to try to avoid getting into poorly designed code and avoid the sort of, make it a class. Obviously, that's better because classes are better. No, they are a tool, just like any other thing in programming. So modular design is an important concept. Everything should be a unit that stands by itself as much as possible. In fact, that ties into the next thing, testing, unit testing. You should be able to test each piece separately. As you're writing it, if you're working on your tests as you write things, often while you still understand how different classes work together, you can still do unit testing, even if you have 3 or 4 classes that must connect. Inheritance is something that's powerful, but you need to be very careful. I have some tips there. Specifically, there's an article here. It's a pretty long article, but it's a really good read. And it's giving you, as somebody who really doesn't like inheritance, I think he's maybe a little bit too heavily against inheritance, but he has some great points. And he does have a few places where inheritance is really important and useful. And he gives you a few suggestions for things that you can use instead of inheritance. Using composition is better than inheritance, etc. So inheritance is definitely not a tool you just want to grab immediately. You want to think about it. Are there ways to avoid it? Specifically, if it starts creating this, what I've been calling a spaghetti mess, where this class depends on this class, which depends on a different class, and you have no idea where anything comes from because there's 10 classes in your MRO, in your resolution chain. And functional design, Python is designed around object orientation, but there are some great ideas from functional design that are worth thinking about. If you don't have time to learn a functional language, then at least use a few of these concepts. One is that classes with multiple states are bad. So you don't want to have, say, an initialize function you have to call, because then the class isn't valid before you call the initialize, and you can't force a user to call the initialize at the programming level. A much better thing would be to do something like this. So this is the bad design. So .cleanup can't be called before init, but this is not forced at a class level. If instead thing.init produces a new thing, and that thing is the thing that has cleanup, that forces you to run in the right order. And that way, this becomes a language feature rather than a social contract that you have to describe somewhere, saying, please call init before you call cleanup.
Sorry to tell you. So I just wanted to do a quick announcement. Sadly, we are missing next speaker, so you have other 30 minutes if you would like. Otherwise, the next speaker could help you to if you would like.
I am happy to talk as long as possible. I could talk all of PyHEP if you want me to. You do not want me to, but
it will be super helpful if I see that you have more sections. So
yes, I was going a little bit slower because someone told me this morning that I would probably cover the
ideal.
Probably have
so
the extra half hour.
Yeah, please go ahead. I will tell you 5 minutes before the end of your
Perfect. Time. Thanks. Okay, and then finally here, just to finish off this, try to make your designs as static as possible. We will cover at the very end, we'll have a brief mention of what static typing looks like. It is very useful, and if you try to do as much static typing as you can, put static types as many places as you can, that will actually push you to better design. Maybe less fun in some ways, but static typing is fun, so that's fine. But designs that are much easier to ensure will work before you even run your code. So anyway, there's a lot of material here. We even skipped a whole section, so feel free to look through this, especially if you're a bit more advanced user. The how classes work and stuff has some other interesting information. So let me take a quick check for the questions. And hopefully some people are replying to these, so I'll mostly look at ones that have not been replied to. One thing I'll point out, just because it'll be useful, and I mentioned it somewhere else. I don't know if we'll be able to cover that in what we do. But someone asked if you can pass X and Y directly in as args. You can't. You have to pass in an object here. That has a .x and a .y. But it actually turns out in Python you can. In Python 3, it's valid to say vector. Can't type. Vector.mag. Now I could pass. I could always pass a instance here. This is the equivalent. Is exactly the equivalent of writing self.mag. This is literally just a shortcut for that. These two things are exactly equivalent. So if I write self.mag, it's exactly the same as calling vector.mag on self. Probably shouldn't name your object self, but say v. So these things are equivalent. But it turns out in Python 3, this is not true in Python 2, but it was true in Python 3, you're allowed to put any object in here for self if it works at runtime. If it has a .x and it has a .y, this will work. So I could create a brand new object that has nothing to do with vectors, but as long as it has a .x and a .y, it works. And that's actually really useful because that means instead of creating a whole bunch of standalone functions like NumPy does, NumPy and NumPy.unit and array.unit or something, whatever thing that is, you don't have to do that anymore. You can now just say, well, use vector.mag on your object. If you haven't, something that's not a vector, as long as it has an X and a Y, it works. And that allows you to have your standalone functions and your class functions in one place. So you have to access them here, vector dot, but you don't have to teach two completely different things. So that was a question I wanted to answer. We will talk a little bit more about static typing. So I'll try to make sure we have a little, because we have some questions coming in for static typing. So I'll try to refer to that. Okay, so let's go ahead. We have an extra half hour, so we're going to go ahead and cover the rest of the sections I claimed we would cover today. Debugging. Let's briefly look at debugging. Might see if I can even adjust this live, but let's try. No, that's not going to be available. Oops. Yeah. Okay. So Python does have a debugger. So let's take a look at code that is broken. Okay. So we've got a function here that's got some bad expression in it. That's going to break. And then we're going to do lots of interesting stuff inside. Inside this, and then we're going to try looking at one of those two functions. So this is a simple broken function, and this is a longer broken function. Okay, and you'll see that we get this 0 division by error, and the traceback is somewhat helpful. It shows you where the error is, but it doesn't tell you everything you might need to know. Here it was really obvious that this function was broken. Divide by 0. I immediately see that. It's not obvious to me looking at this that x is 0. So in order to do that, you can run the debugger. So IPython has a built-in debugger. It's using the PDB, which is built into Python, but it gives you a little interface. And it even has a trick that's really useful. If you use this magic statement, so it starts with a %sign and the word debug, usually you can avoid if that's the only word you write, it'll guess that you mean the magic variable, and you don't even have to write the %sign. And it'll start up the debugger. So if I do P, which is print, it's got a little mini language, you can look it up. It's the PDB. So P is for print. Print Y. Y is 8. I can print X. X is 0. I'm doing X divided. If I'm doing Y divided by X, I'm doing 8 divided by 0. I can see why this failed now. You can even step forward and backward, move around, do various things like that. You can even, Q is quit. You can even put in a breakpoint. Let's put the breakpoint here. Okay, that's a Python 3.7 feature. There's a pretty easy way to get it in Python 3.6. You just can't use the nice word breakpoint. So if I run, oops, sorry. It starts the debugger again. So if I run this, now when it hit that breakpoint, it stopped and dropped me right into the IPython debugger for me. So now I can say py, y is 4. I can do next. That jumped forward a line. So now I can do py, y is now 8. I can do next, and I can jump along and see things. So now I'm right before I've run this line. I'm going to quit that again. Okay. And it just told me I quit. That's fine. So that's a little built-in debugger there. Rich also has a traceback feature, which is quite nice. This is technically, I think, not required anymore. Let's try it. So I'm going to install the rich traceback handler. So rich.traceback.install. I'm also going to turn the show locals features on because I think that looks really nice. If you have secrets in your locals, you probably shouldn't turn it on. So there we go. So now my traceback looks like this. And actually fairly recently, it was very recently, they added support for this to the notebook too. But this is what it would look like in a terminal as well. And you'll see that I show locals, so I actually see my locals right here. And the traceback is showing me the locals for each line, giving me nice colors, complaining about one of the files not existing, it's fine. And then it's doing this. So that can be very, very nice. You can use this if you're in a sort of end use case. Don't put this in a library because you want your library user to be able to install their own or to see the regular tracebacks. You don't want them to be surprised with this because they may have their own traceback handler they want to install. Okay. Also, there is a built-in debugger. I'm going to skip it for time, but there's actually a built-in debugger in Jupyter Notebook. It doesn't work with the IPython kernel just yet. That support has just been added, and it might already be there in what you have, but it should be showing up soon. So there's actually a visual debugger built into the notebook that shows you things. It's definitely worth checking out. Okay. Let's take a quick look at profiling. There's a line profiler tool that you can install. That's really nice. There's actually a built-in C profile as well. But the line profiler I find is much nicer. So this is a little example of a function. This is a Monte Carlo sampler. And I did not install SciPy in here by default, but a great example is if you try to use scipy.norm instead of numpy. So we're just going to write this. We're going to write this out to a file because it had a little trouble reading this in as a cell. So I'm just going to write it to a file and then load it from that file. And then I'm going to run the line profiler. So load extension line profiler. It actually has a nice IPython extension. And this is the IPython extension. You can do line profile. You give it the function you're interested in, so it knows what to show you, -f and then sampler. And then you give it an expression to run any expression you want. It'll do that, and then it will profile this. There we go. And it'll show you how long it's spent on every line. So that's why I like the line profiler, because by line is a bit more natural, I think, than by function, which is what the built-in one does. And you can see that if you're going to try to optimize this, you should only optimize what is slow. You shouldn't optimize everything because you want to keep your design nice and easy to maintain and read, and only optimize the slow parts. I should spend my time here. One thing I would be really tempted on just reading this function would have been to work on this, because that's appending to a list. That should be slow. Well, it's really only spending about 1% of my time appending to that list. So, I could change this to make an array beforehand, but it's really not where my time is being spent. I'll gain 1% by changing that. The thing I need to spend time on is trying to optimize this. So I could use Numba, for example, and optimize that, and that would give me 70% of my time. So this is what I should target. Okay, and I don't have a section on memory profiling here. It's a little harder to do in a notebook, but I gave a link there to a post giving a description on how to use fill for memory profiling. Okay, so let's spend some time on static typing. This is something I really wanted to get to. Several people have had questions. Let's check the questions actually first before I go. Someone asked why they can only enter 160 characters. I assume that they're probably into Slido. That's probably trying to mimic Twitter. I don't know. And then someone asked, does debug only work in an interactive Python session, or can you use it? So debug would not make sense in a script, and I'll explain why. So if you're in a notebook and you run this function, it fails, but the notebook keeps going. You can keep typing in cells. So debug just jumps you back to that last cell that failed with the quit. Or if you're this also works inside the regular IPython terminal as well. It doesn't have to be a cell. But it just jumps you back there. If you're in a script, if you have a crash and you don't catch it, it exits. So there's no way you couldn't call a debug later. You can run an .ipy file, an IPython file. I have no idea if and magics work in those, but I don't know if debug would make sense or not in those files. But if you are doing this and you have a crash, there are still ways to do that, still ways to get this out from a file. There are ways to catch that error and then start a debugger. So you can still do it, but you can't use this magic here. And one of the most common ways is You can run it directly from the debugger, PYDB, you know, and then run the file through that. But you can also just stick a breakpoint right before the crash if you want. Okay. All right, so let's take a look at static type hinting. So it's really one of the most exciting things that's happening in Python right now. This has been a huge push ever since roughly 3.5, I think, is when they really started pushing into this. And this was sort of an idea when they started Python 3.0. They added this syntax that allowed you to put some random object, anything you want, as an annotation for a variable in a function and as a return annotation. And they were definitely thinking about types as possible, but they weren't sure. They kind of put it out there and they said, well, let's see what people use them for. And one common use was to say, well, I want to show you what types I'm using. It's very natural. It comes from other languages, and it gives you extra information. It is extra visual clutter, but it gives you extra information about what you're expecting and what you're expecting to return. They do nothing at runtime. Static typing does not affect runtime. So for example, if I do F and I give it the string, the list high, it gives me high, which was probably not what I was thinking about at all when I wrote this function. I was thinking I'm going to be multiplying integers. But again, it let me do it at runtime. There's no restriction here. So there's no harm in adding static typing. It's not going to break anybody at runtime, so you should feel safe adding it. But it gives you an idea of your intent, and there is a place where you can use it. One place you can use it is using MyPy. So let's write this out to a file. So this is just what I wrote before, but I'm sticking it in a file. And now I'm running MyPy on it. So in a notebook, if you use an exclamation mark, that just runs something on the in the shell. So I'm just going to run MyPy on this. And so if I do that, then it tells me, hey, argument 1 to F has an incompatible type. It has a list of strings, but I expected it to be an integer. So this is invalid at static type check time. You could think of this like the compile phase of a compiled language. Since Python is interpreted, there is no compile phase, but you can add one manually. And that's the static type check time. This MyPy run. Okay. And so this will keep you truthful to your types if you run MyPy. Okay. And the most important thing is we didn't actually have to run any code to see this error. I didn't have to deploy this and see it crash on a grid job. I saw it before just as a static step. This code could be code that can't run here. Doesn't matter. MyPy can still check it. It could be slow code. MyPy checks it immediately because it's analyzing the source. So it's very, very, very powerful. So let's take a look at a potential error. This is actually one that's surprisingly common. This is one that MyPy catches all the time, and it's a real error in your code. If you write a function like this, and it can take F, or it can take an integer or some value, or none, which is, we commonly use none to say, well, it's default, or it's something that can be passed in. But using it like this is actually an error, because what happens if I were to pass none in here? Well, if X is none, none times 5 is invalid. It's not a valid expression. So it will force me to say, well, I need to say if X is not none, return X 5. Okay. All right, now it's complaining because it's forcing me to be truthful here. Now this is technically valid because, but it's a really bad idea. Because technically return none is a valid return, but it's not clear to the user that that's happening. So MyPy actually does enforce that. So now it's happy. So now this can take an optional. It will not crash at runtime for anything that I list here, which is what MyPy does. So now it will not crash at runtime, regardless of what I give. Okay. None, somebody did ask about this, and I wanted to get to this. They noticed that none seems to be special because another way to write this would be this. This will actually only be valid. All right. So if you want this to work in Python 3.7, 3.8, or 3.9, I think this was added in 3.10, maybe it was added in 3.9. Then you have to write from future import notations. So what that will do is it will turn these into true strings. These will never be evaluated. I can put invalid syntax here as long as it doesn't interfere with the function definition. And it will just turn them into strings. And MyPy is perfectly happy with this. If you do it in Python 3. If you do it in the right mode. Python, that. What's the? I usually set this in a config file so I don't think about Python version. Okay. Version equals 3.7. Wait, why is it still? 4. Is this an old version of MyPy? Oh, it's an old version of MyPy. I don't know how I got that. Okay, so in MyPy 0.800, it actually does this. I don't know why I have an old version. Oops. Ah, because this is not running inside my virtual environment. Live debugging here. I should have installed, you shouldn't have this problem because you should have the regular MyPy installed. There we go. Okay. So this command is not running inside my virtual environment, which is level up your Python. I have no idea where it's grabbing 7.9 from because I shouldn't have that sitting anywhere. I do. So now I should be able to run that. Oops, except I need to give it a file. Leave that. Okay, now it's happy. So they notice that none is being used like a type. This is special in Python. None is allowed instead of type none because none is its own type. And so they did add special support to the typing proposal for none. And I would really like them to add a couple other things to this special support. I really want to see ellipsis added because currently that's really not handled well. So ellipsis really should be added to this in my opinion. But yes, none is special. So this syntax says int or none. So it's the same as saying a union of int and none, which is what optional is. Okay, but this will only work in Python 3.7 because this only exists in 3.7 and newer, even though this syntax itself is either as new in 3.9 or 10. Okay. But you can use it in type annotations, which is really nice. Okay, so adding types. Oh, and someone was asking about the word optional. I know some people who love this expression and hate the word optional because optional means it could be none. But there's the idea in Python of an optional argument, which often is one that could be none, usually say equals none. But yes, those terms are in conflict. Anthony Solittle, I know, hates this term, and he loves, ever since Python 3.7, he loves switching things to this, because this clearly says my type is int or it's none. There is a discussion on potentially adding this syntax to say int or none, just as a quick, maybe an int syntax, but that's not added, and I don't know if it's ever going to get added because it's kind of a weird, it's the only postfix operator we have in Python if it gets added. But there's a discussion to do that. It would also obviously conflict with IPython's nice help system. Okay. So adding types, you really should usually add these in line as annotations. As long as you're in Python 3 code, that's fine. You can also add special type comments. That's almost entirely for Python 2. And there also are special, you can do a PYI file, which is a type only file. It looks like a header file in C++. There are occasional reasons for that. If, say, a file is generated or a file it doesn't actually exist and it's actually a shared object library or something, that's how you would add the types, is using a PYI file. You can even ship a package that's all types with these PYI files, but those are called stub files. And they just have the type information, and that's it. If you look at the standard library in Python, they actually don't put types in. Those are added as stub files. So all the stuff in the standard library actually exists somewhere else in a library called TypeShed, and they're all stub files. But for your code, most of the time, you want to use them inline as annotations.
Henry, we have 5 minutes left, just in case.
Okay, perfect. I'll just speak for another 2 minutes, then I'll answer the rest of the questions. So generally, you shouldn't. MyPy will. Oops. Sorry. Yes. Okay. So generally, MyPy will do as little as possible. So it will ignore anything that's not typed, which is not necessarily ideal. It means bugs that can slip by because it's not checking everything. So you can add configuration. The SciPy, the PyHEP developer pages have a nice section on MyPy configuration, and they now have a page on MyPy as well. That was heavily based on this material. So you want to be adding types as many types as you can, and then you want to start making MyPy stricter. In fact, you can even add the -- strict flag, which will make it fully strict, and it'll complain about absolutely everything. Yes, so unions are a new syntax coming in Python 3.10, so that's not out yet. Generic types are the 3.9 feature. So this is sort of what a piece of type checked code looks like. It's definitely a bit more verbose. You have things you're maybe not used to seeing, but it's really helpful because if you're reading this code and if you don't understand what's going on, knowing what these things like X, that this can be a string or an integer, really helps you understand what this could be. So it's a good thing to start sort of getting used to seeing those. And then if you're using them, MyPy can tell you if you're using them incorrectly. So it's really nice. It's really powerful. This will actually not work because of that weird MyPy. The second line will not work because of that weird MyPy thing you saw earlier. But this is what it looks like if you're 3.7 or newer. This was added in 3.7, and now you can use all of the nice shiny new features that are in 3.9, 3.10, features that have not come out yet, and you can use them in your type annotations, which is really nice. Because type annotations are rapidly getting better. So things like this is now much more readable than this, in my opinion. This is just the regular list bracket int. It's not this special list type. Notice I got rid of all my imports. I don't even import anything. This is all just native Python now because of this from future import annotations. Or if you're running Python 3.10, this will just work without that because this will be valid. All of this is valid in runtime in Python 3.10. Okay. And I'm not going to run this because it'll actually fail because for some reason I'm getting Python, MyPy .790. Okay, and I'll let you read protocols on yourself, but this is also a really useful thing. All right, any questions here? MyPy. Hopefully people are replying to some of these questions as well. I'll look at a few of the ones that don't have replies. How well are types supported by the community? They are becoming much better supported. there are a lot of type packages. So if some of your favorite packages don't have built-in types, somebody's probably written, usually the MyPy people, have written something for it to add types to it if it's a really popular package and the user doesn't want to support types for some reason or doesn't know how to, etc. Certainly in high energy physics, they are starting to show up more. Boost histogram fully supports types. HISTs fully support types. The unit package fully supports types. Particle, I think, is either fully supports or partially supports types at least. So we're starting to get these supported, and it's just because this helps you. It's such a nice help. Any more questions?
I think we can move in case
I think we're ready to move on. Everything seems to be being answered. Yep. Okay.
But in case there is a Slack channel, I think dedicated, and we are planning to post their questions as well that were already in Slido. So, yeah. Thank you so much, Henry. It was really amazing. You covered everything, almost. So we are looking forward for your second part of the tutorial tomorrow, right? And yeah, so I would like then to move to our next speaker, Vincenzo from the ROOT team, who will be talking about distributed RDataFrame and Python package that was developed to enable it into the analysis. Vincenzo, you have 30 minutes and I hope you can share screen.
Hi, yes, let me try and do that. Okay, can you see it?
Yes, wonderful.
All right, thanks. So thank you, Oksana, for the presentation. Yeah, today I'll try to discuss about this Python package that we've been developing in the ROOT team for RDataFrame distributed analysis. So the layout of the outline for today's presentation is roughly like so. I will present briefly what is RDataFrame, and then I will discuss the steps and the goals that we had in mind for a distributed version of such a tool. There will be some time for demonstrations with Jupyter notebooks on Swan, and I will show you later that. And then just to conclude the discussion, I will present you some performance numbers that we ran and a summary. All right, so RDataFrame is this Pandas data frame-like high-level interface to high-energy physics data. It features a declarative interface, and with this declarative interface, you can define a set of operations to run on an input data set. And RDataFrame supports various data sources to that purpose. And in the end, the set of operations that you have defined will actually be executed lazily. That is, they will be accumulated in the program and not run until the moment where you actually need the final result. At that moment, all the computation graph that results from the operations that were requested will be executed in one go on the entire data set. So the final result will finally be retrieved. And the goal with this interface is to provide an easy-to-use way to process high-energy physics data across the board. And for that, in this slide, I also leave you here down the reference guide and some tutorials that you can check out for yourselves if you're still not familiar with RDataFrame. Now, RDataFrame itself as natively support for exploiting all the cores available on your laptop or on any single machine. So it does that through implicit multi-threading that is available in ROOT. But there's another goal that we had in mind, and this goal was to enable interactive and large-scale data analysis with RDataFrame, but distributing the workload of the analysis to a set of resources that might be remote, outside of your own laptop. So in order to do that, we needed to separate a bit the roles. So the RDataFrame computation graph that I previously described is built locally, and then the workload that's represented by this computation graph will be distributed to a backend, to a kind of distributed framework. For example, we already have some working implementations of connecting to an Apache Spark cluster and also a Dask cluster. And these are the two backends that I will show today. But the design of this Python package that we have created is modular. And in fact, many other backends could be created and implemented in a way that it would allow RDataFrame to plug in to any of these distributed frameworks. For example, we are also developing another, with an external contribution, we are developing a backend for AWS Lambdas, so running the RDataFrame computation graph on these serverless functions. But that's not the topic for today. Today, I will just discuss the first two that you see here. And the final goal for this is to have everything from start to finish in the same interface. So you don't need to, I don't know, take your time to launch the job and then wait for the partial results and then merge the partial results on your own. Everything is done in the same Python program in the end. And how does it look like from the perspective of the program, so the user? In this slide, I wanted to show you the main differences between writing and creating and running an RDataFrame analysis locally on your single machine. And this is what you see on the left. And then on the right, I try just to highlight the few differences that are needed in order to turn this Python program with RDataFrame into a distributed execution. So on the left side, let's start with importing the class that is RDataFrame, and you can just import it from the root package. And then whenever you have imported this class, RDataFrame supports some constructors, and you can provide the arguments to these constructors directly from Python. Even though RDataFrame is a C++ class, but we'll get to that later. So in this case, you see that there are two constructor arguments. The first one is just the name of the dataset, and the second one is the name of the file where the dataset is stored. And let's quickly jump over to the right side here to see how to turn this into a distributed analysis. You will see that the differences are very minimal. The thing that you need to do is that instead of importing directly RDataFrame, you need to tell root that you want to use a distributed RDataFrame. So these things live in their own root submodule. For this example, I just wrote the code to retrieve a Dask RDataFrame. So you see there's distributed.dask.RDataFrame. And you can just, for easiness, you can just store into a variable. So later calls to RDataFrame will actually point to the distributed RDataFrame class. And then the extra step that you need to do is whenever you're creating the RDataFrame, you just need to provide it with a way to connect to the Dask cluster in this case, or the Spark cluster in another case. If you're already familiar with any of these distributed frameworks, for example, Dask, you will know that you can create these client objects, and these are just Python objects that allow you to connect to the Dask cluster. And then the RDataFrame constructor, of course, will always accept the same arguments as the local RDataFrame constructor, as you can see here, the name of the dataset and the file name. But it will also accept an optional argument for this connector to the distributed cluster. In this case, we have a Dask client optional argument that will accept an object of type client from the Dask library. As you can see, there's a third box down here. And it's just one, it's not two. And the reason for that is that apart from pointing it to the right RDataFrame class and connecting to the Dask cluster, everything else in the program stays exactly the same, from local on a single machine to distributed execution on hundreds of nodes. There is no extra step needed in the code to retrieve your final results. So that's what happens in the program itself. But behind the scenes, the creation of tasks for these distributed resources is actually done in this way. So in this image, I just wanted to show you that we, on the client side, we are creating the tasks that will be sent to the distributed resources, and we are doing that by splitting the input dataset into some ranges of entries, and we take care that the ranges do not overlap one another. So this is just a list of pairs of integers, right? And this list will get sent to the distributed resources. Each element of the list, each pair will create a task, and each task will be run in one of the machines of the cluster. One of the important things here is that the tasks will never overlap, also with respect of the reading. So it's not like each task will have to read the full data set. It will just have to read the particular entries that were assigned in the range, and this also avoids extra overhead. So now that what I just showed with this distribution of the tasks is, generally speaking, what any backend in distributed RDataFrame should do, but it also, of course, needs to be actually implemented. And here in this slide, I wanted to highlight some differences in the implementations that we found when dealing with Apache Spark or with Dask. Well, simply speaking, we are always creating a sort of a MapReduce tree pattern in the execution of the tasks in the distributed resources, something that you can see here on the right side of this slide in this image. So there will always be a set of mappers. In this image, only the first vertical set of nodes is the mappers. And then all the other nodes in the distributed computation graph will be reducing nodes. So nodes that take the partial results of the mappers and then reduce them until there is only one final result that can be sent to the user. That being said, this similar distributed execution is, well, it's just adjusted to the API of the backend itself. For example, with Dask, we needed to use the delayed objects, or with Spark, we just used the native Spark API. But in the end, what we create is what you see here in this image: a set of mappers and all the reducers that just need to merge the partial results. One other difference between these two backends in particular is that Apache Spark processes everything in stages. So with Spark, you get all the mappers that execute all their work, and then at a separate stage, you will just reduce these results. On the other hand, Dask can reduce two mappers that have already finished their work without waiting for all the other mappers. So that happens more in a more dynamic way. But these are, just implementation details. The important message is that we're always creating this computation graph that follows like a tree pattern in the end. And another key message that I wanted to discuss is the following. So with RDataFrame, we are able to connect to Apache Spark, Dask, or any other kind of backend through their Python interface. And we do the same with RDataFrame because Root offers a Python interface that's called PyRoot. So we can glue the two interfaces together. But in reality, when we are in the distributed resources and we are running the operations that the user asked, we are actually running C++ code. And the C++ code does mostly everything, like the bulk of the operations, the computation graph and the IO, everything is executed in C++ thanks to Root and its interpreter. Okay, so that was a general introduction about distributed RDataFrame, and now it's time for a demo. So for the demo, you can see in this slide a link to the notebooks that I will show you. There's a GitHub repository. And this GitHub repository will also have a little badge. Probably I can already show you this way. So if you go into this GitHub repository, you will see a badge down here to open this in Swan. I have already opened my GitHub repository in my Swan session. Swan is this service for web-based analysis that CERN offers, and you can see it as this interface, which is quite similar to the Jupyter Notebook interface. And it's very nice to execute these notebooks that we already had in the repository. So with the demo here, I want to follow a physics analysis example that we have here, And I want to show you how this example can be run locally with RDataFrame and then with distributed RDataFrame, both on the Dask, with the Dask backend and with the Apache Spark. So the analysis itself is processing a single file that stores 61 million entries. These events were recorded by the CMS experiment in 2012. So the analysis itself is an open data analysis that you can find also links to in the notebook itself. And here we are just starting with importing root, and then we need to create the RDataFrame object. Again, this RDataFrame object is actually at its core is a C++ class, but we are accessing it through Python thanks to the PyRoot bindings. And you can see that we have two arguments to the constructor of root RDataFrame. The first one is, again, the name of the dataset, and the second one is the path to the dataset itself. Once we have constructed this RDataFrame object, we would need to analyze it. There is a particularity in this notebook that since we are running locally and we don't want to run on 61 million entries because that could take a while, we can just tell RDataFrame to only operate on the first million entries. And we do that through the range operator here in operation on RDataFrame. And then we are actually starting the real analysis. So the analysis is made of the following steps. The first steps are filtering the dataset, and you can see them in this cell here, filtering the dataset from unimportant events. And then whenever we have the imported events left in the dataset, we want to define a new column. And this column will be the result of an operation that's made on other columns of the dataset. This operation is actually written here, and we are calling from PyRoot, from Python, from this Python interface, we are calling a function that is inside a root namespace. So this function is actually a C++ function that's implemented inside root. And we are creating a new column in the dataset thanks to this define operation in RDataFrame. And then finally, we want to retrieve the final result, which is the histogram, an histogram of this column that we just created. Now, if you haven't noticed so far, we never got a cell that was running for a noticeable amount of time. And that's because, as I mentioned previously, RDataFrame just runs lazily. So until we request this histogram, which is the actual final result that we want, we will not see anything running. That happens, the request of the histogram happens in this cell. So I can execute the cell and wait a few seconds for my result to come back. Okay, here it took 3 seconds. And then finally, I can plot the resulting histogram in this other cell with JS root that enables these plots directly in the cell, in the cell of the notebook. Okay, so this is the final result of the analysis. In this case, I want to reiterate that this result does not contain the full data set. So we didn't process the full data set, but we just processed the first million entries. Now I will move to another notebook which has
Vincenzo.
Yes.
Sorry. Yes. Couple of. I know. Oh, very sorry. I mistake with time. I think you have actually 12 minutes. Sorry.
Okay. So I will move to this other notebook. This is the same exact analysis as we just saw, but I'm going to use what's it called? I'm going to use Dask to distribute the execution of RDataFrame in this case. So, and in this case, I will be able to not just select few entries from my dataset, but actually run on the full dataset. Now, to do that, let's see only the differences between the two notebooks. So one of the key differences is here in this cell. We are creating the object that is the object that will allow us to connect to the Dask cluster. And this object is the client object that you see here. We are connecting to a cluster of Dask machines of Dask agents that we have created specifically for the purposes of this demonstration. And so we have it available in the CERN network with 16 workers and 16 cores in total. Now, with this client object, we can go and create an RDataFrame that will be able to actually distribute the execution to Dask. And to do that, we just need two more things. The first one is to tell root that we want to use the task.RDataFrame class, and then actually create that RDataFrame using the first same two input arguments as the RDataFrame of the previous example. And then we have another two optional parameters. The first one is called end partitions, and it's just the number of tasks that we want to run. So in this case, we are running 16 tasks. That means that each core of our distributed cluster will have its own task to run. And finally, as I mentioned in the slides, we need to give it the client object. So the object that will allow us to connect to Dask. And whenever we have done this, we have created the RDataFrame. All the rest, all the cells, they are exactly the same as the one that I just described. So I won't go through them again. We are creating this new column and trying to create an histogram. But this time, whenever I trigger the execution of the creation of the histogram, it will not be executed here. But as you can see, if I move to this other tab, it will be executed on the Dask cluster. And this is the tree pattern of the MapReduce execution that I mentioned previously. And in this Dask dashboard, we can see, well, it's probably already over, but we can see the status of the cluster, and we can see that Dask was able to run these mappers, these tasks quite fast. So if we go back to the notebook and we try to plot the result, we can see that now we have the full data set having been processed, and the plot that comes out of that is available for us. And we didn't process just 1 million entries, but the full data set. So as a final demonstration, let me show exactly the same thing, this time using the Spark cluster that CERN offers. So in order to do that, we already have a graphical interface that allows us to connect to this Spark cluster in Swan. And it's here where the Apache Spark symbol is placed. And then we can just connect to the cluster with this connect button here. I chose to have 16 cores in total, again, the same as the Dask example. So connection just takes a few seconds usually. And whenever it's connected, it will tell us that we can go back to the notebook, and that it also has created, okay, here we are. So if we go back to the notebook and we, start with importing root as usual. But then what I wanted to show here is that the connection to the Spark cluster is given by an object that is called a Spark context. In this case, since we connected to this cluster thanks to the graphical interface, we already have a Spark context provided for us in the notebook, and this is provided by Swan. If you had your own Spark cluster, you could just create the Spark context on your own, and everything else would work just the same. So again, we need to create the RDataFrame. So we point RDataFrame to the correct instance. In this case, we have a Spark RDataFrame. And we can create the RDataFrame with the same constructor arguments, but this time we're not using Dask client as an optional argument. We're using Spark context because, of course, we're using Spark. So we create the RDataFrame that can run on Spark. The rest is exactly the same. Again, I won't go through that. And we come at the cell that triggers the distributed computation. So whenever I'm in this cell, I can start executing it, and Swan will start to provide us with a Spark UI down here. So we don't have a dashboard in another tab, but we have it just here in the notebook itself. So in the Spark UI, we can go see the actual Spark tasks being created and started. So you see some of the tasks are already there, and we just need to wait for the Spark executors and the Spark workers in general starting to address the tasks and run them distributedly. Whenever a task is over, we can see that they start turning green. And in a few seconds, we should be already seeing the completion. Okay, exactly. There we go. And finally, we can already plot here the final plot. So we have just shown the differences between running an RDataFrame analysis in a local notebook, so in a notebook local to your machine, or in a notebook that connects to a Dask cluster, or in another notebook that connects to a Spark cluster. And the differences in code were actually quite minimal. So now we can just go back to the slides for some final remarks. And I have some numbers to show you. All right, okay, I can switch back to full screen. So that was a demonstration, but we also ran some numbers to test the performance of the two schedulers. I created, as I mentioned previously, a cluster of OpenStack VMs. In total, we had 13 VMs. All the VMs have the same configuration that you can find here. One was reserved for the Dask scheduler or the Spark master, and the other 12 VMs were always reserved for running the Spark or Dask applications. The dataset itself and the analysis in general is exactly the same. The only difference is that I replicated the dataset 100-fold to reach a dataset size of 210 gigabytes in total. And this dataset is being fully processed. So all 210 gigabytes are processed by the Spark or the Dask agents whenever I run the distributed RDataFrame application. And let me just show you the results of these performance numbers. So in this slide, I am showing the average execution time of the run of the analysis with the increased data set with the Dask backend of distributed RDataFrame. On the left side, you have the absolute runtime. These are averages over 3 measurements for each of the data points on the x-axis that represent the number of nodes that were used as agents, as workers in this example. And on the right side, you just have the same numbers but turned into speed up. So the speed up compared with executing this analysis on only one node. And if I go to the next slide, I will just show you the same plots, but this time with Spark. As you can see, between the two schedulers, the difference is not that great. Spark seems to be a bit better on the speed up point of view, but it's also maybe because we had this slightly higher runtime in the execution with one node. So we wouldn't say that there's a real gap between the two schedulers, sorry. And just as a final comparison, I have this other plot where I show the full distribution of the points of the benchmarks that I ran side by side. You have the blue circles that are representing Spark and the yellow circles that are representing Dask. And as you can see, both distributions, maybe except for this first point, but all the others, they reach quite a similar runtime. So that's exactly what we want. So in summary, I have presented you RDataFrame, which is Root's declarative interface for data analysis. And since the latest Root release, which is 6.24, RDataFrame can also run on distributed frameworks, such as Apache Spark, for example, requiring minimal changes with respect to a local application of RDataFrame running on a single machine. And for now, we have, I've also shown the implementation of 2 backends today. One is Apache Spark and the other is Dask. There will be also other backends coming in the future, and stay tuned for that. So I also leave you in this slide some useful links, the guide to RDataFrame and a tutorial if you want to try out this feature for yourself. So yes, that's it from my side. So if you have any questions, I should probably see on Slido actually, right?
Exactly.
Cool. Let's see. All right, so I'll start from the first one. Is it possible to use RDataFrame with multiple T3s and the same number of entries? So if you're referring to using RDataFrame, for example, with the friend trees, yes, that is definitely possible. Traditional RDataFrame, the RDataFrame that runs locally, has support for that since many Root releases. Distributed RDataFrame is also supposed to have support for that. If you try it and you find anything that's not working as you would expect, please let us know by contacting the Root team or submitting a GitHub issue. Yeah. Do we have to do something whenever I answer? Like, no, just leave it there? Not sure.
Yeah, leave it. Yep.
Okay. Cool. Question about distributed RDF. How does it compare with going to batch, like htconda? To process large data set, I had to go to batch. So curious to try. That's a very good question. It's actually an alternative to going to, so you know, batch systems and interactive analysis systems like Spark and Dask, of course, they have differences and they serve different purposes. But you are right in thinking that both are ways of distributing your application if you have a very large data set and you want to process a very large data set. One added benefit with systems like Spark, Dask, and in this case, distributed RDataFrame, is that you can do everything in the same interface. So you don't have to submit your jobs, then wait for the partial results, merge the results. You cut that middle step, and you just have everything in your own Python program or Python notebook, and you will get the results straight away there. Okay, so next question. What are other applications of RDF besides using CERN Open Data? Well, I would say that RDataFrame is suited for any kind of data. I mean, I have also shown a slide here. Let me go back there. So in this slide, for example, I was showing that RDataFrame has support for different kinds of data sources. Of course, you would need to adapt your, I'm not sure about the data source that you have in mind. If it's in this list, probably RDataFrame will support it. If it's not in this list, it will not be supported, but you can always make a request for adding a support of a data source, since different data sources can be added and supported in RDataFrame. So far, with distributed RDataFrame, we have tested it with the T3 data source, which is Root's default data source. We haven't tested it with other data sources. Maybe in the future we could also think about that, but keep in mind that for now, distributed RDataFrame is an experimental tool inside the Root framework. So some things might still be missing, of course. All right, so next one. Is data read from EOS by each node separately? IOW, do IO bound analysis get a speed up? Yes, definitely. As I was trying to explain in this other slide, what's that? This one. So distributed RDataFrame works in such a way that each of your tasks in the distributed resources will read only a specific portion of entries. Let's say your dataset has 100 entries and you just want to read the first 10 entries in a task. You will not read the full 100 entries from your dataset in that task. You will just read 10 entries. And yes, you will also read them remotely. But again, you will not be reading a full file from remote, but just that particular range of entries that you like. And this avoids extra network transactions, of course.
Let's go with the last question, and then in case we can move to Slack. So, yeah.
Okay, thanks. So last question then. Is it possible to use precompiled C++ defined filter kernels? This is a very good question. We are actually actively discussing and working on that. Currently, RDataFrame supports, as you have seen in the slides, passing strings, and these strings need to have inside them valid C++. So whatever you pass in this string, and if it's valid C++, it will be turned into a C++ lambda and just-in-time compiled. But the direct answer is that RDataFrame runs C++ code. Now, an added side to this question is whether you could run maybe also Python functions and pass them to these defines and filters. And that's something that we are still trying to figure out. We traditional RDataFrame has support for something like Numba that is used to actually wrap these Python functions and be able to JIT them. Distributed RDataFrame still needs some work on that side, but definitely you will always get your RDataFrame running C++ kernels, even though you access it from PyRoot.
So,
all right. Yes.
Vincenzo will invite you to Slack if you're not there.
Yes, I'm there.
I think it's a channel topic. Ben, which is
fundamentals.
Python for
Hi, everyone. So it's time to get back to our second and last session of the day. So you may have seen this is a special session this time. So we have a series of lightning presentations. So this is nominally 8 + 2 minutes with some flexibility, right? So the idea is really to have a very focused advert or hello world presentation on some cool things. So please for all speakers, do keep the time, because we realize for some of the people connected, this is already the evening. So let's start with Hans, who will talk to us about the Monolens. So please go ahead, Hans.
Yep. All right. So you should see my slides, which are not full screen, which is intentional. All right. So let's get right into it. So this is about Monolens. It's a small tool to view part of your screen in grayscale or in simulated color vision deficiency. Why did I make this? So reviewers were asking us, please make your plots visible in black and white print. Maybe you know this. So this was in our current HCB paper that we are about to publish, and I wanted to have a quick way of doing that. Yeah, so and the other thing is, if you ever do graphical interface design, you want to make sure that your color themes are friendly to people who have color vision deficiency. We actually had this case for the iMeaning Jupyter interface. Yeah, so if you want to use Monolens, it's easy. You can just pip install it, or if you are familiar with pipx, you can just pipx run it. It's written in pure Python. It uses Qt for the GUI part and NumPy and numbar for the numerical calculations. It works on OS X and Linux and perhaps even on Windows. In principle, it should work because all these things are platform independent, but it's untested. And it's easy to use and it's fun to use. So let's just play around with it a little bit. So it just creates a small, so I'm opening it now in the shell on another screen. So now you should also see this little thing that I can move on top of the slide, and then it turns everything into grayscale. And I put in here some macrolit plots, which are with the default colors, and it's quite interesting. So in black and white, you have problems discriminating the bottommost one from the top one, maybe. And you can also press tab and then go to, so this was grayscale mode, and now it's red weakness. So now you see that the second color and the third color are almost indistinguishable. And if you go to green weakness, then the uppermost colors are almost indistinguishable. So yeah, so this is the point here to easily see that. You can also apply this here to these Ishtar plates. So in red weakness, you don't see the numbers anymore. All right, so that's all. I mean, that's all it does. Let's close it again. So since this is PyHEP, I also want to give you a small look under the hood because this is interesting. So what Monolens actually does, it makes screenshots to give you an illusion of a filter. It's not possible for an app to act really as a filter on your screen, because apps cannot read the pixels under themselves. Maybe that makes sense, right? So if you don't hack into the window manager, you cannot do that. And this is a normal app. So this only works for static content. I can actually show you how it fails easily. Let's run it again. So if I switch slides now, you will see it still has the old image here. So, but if I move it around a little bit, it updates, and now it works again. Yeah, so that's how it works. So as you move the lens around, the screenshot is updated. And this is actually quite a challenge to do in real time, because if you have a full HD device, as you probably have, and if you have a Retina device, it's even more pixels, then you have 8 to 20 megabytes, and that you want to have a certain number of frames per second. And yeah, if you color convert this in real time in Python, you will have a problem. It actually works if you use NumPy. And you use some simplified color conversion code that I took from another project, which is just basically vectorized adds and multiplies. So in all, this is an embarrassingly parallelizable problem, and it also profits from SEMD, which NumPy also uses already. But you can make it even faster when using Numba, as you see in the next slide. So unfortunately, PySite 6 does not have a NumPy interface, but this QImage supports the buffer protocol, so you can actually hack into the memory of the image and do all these nice things here. And here are two functions to do the color conversion. This is how it looks like. So it's basically this part here. And if you do it in NumPy, that's it. And if you do it in Numba, that's it. So you just, it's almost the same code. You make a little for loop here and apply the parallel option here. And then it works 20 times faster. Yeah, this brings me to the conclusion already. So Numba rocks. That's one of the takeaways here. And if you have never thought about this, so color vision deficiency is actually not rare. So it's 8% of European males. Females are less affected, because they have two X chromosomes, and it's only if it's only deficiencies only on one of them, they can compensate with the other one. So yeah, what does it mean? 8%. So that's 1 or 2 persons in an average seminar room of 30 people. So it's really something to take into account. It's easy to forget if you don't have this deficiency, but it's also easy to fix if you're willing to tools like this. Okay, I'm a little advertiser about my other projects. So Monolens is just a tool, a little tool, but I also have some more serious things like boost histogram, and we also have a Python web panel, and I need PyHEP, and recently I added this or worked on this resample library a lot, which implements bootstrapping. Okay, that's it. So how do I do this with the questions now? Should I just read them out? So how?
Yeah, do you want to check immediately on the slide, or shall I share it? It might be easier if you have the link. Do you have it?
I mean, I have it open, so I can just read off the question and then answer it.
Yeah, that is easier.
So the question is, how operating specific is this? So I mean, in theory, it's not operating system specific, because one of the great things about Qt is that it is abstracting over all these things. Someone said it's really cool. Thank you. But I mean, in practice, so I had to really try it out. And so I have 2 computers here at home, one Mac and one Linux system, and I had to try it on both of them. I mean, debugging graphical apps is really a pain, right? You have to just try it out. You cannot do this automatically, or at least I don't know how to. And I really noticed a lot of things where the abstractions were broken, and I had to really very carefully use the Qt API to really have this property that it's part of independent. So I mean, since it works on 2 systems, it might also work on Windows. So if you have Windows and you have Python installed there, give it a try and let me know whether it works. Could this be used the other way around? Make it so that people with color deficiency can disentangle the colors? Yes. I mean, not this app, but in principle, this is possible. There are libraries which do exactly this. I mean, if you know how the deficiency works, you can enhance the colors in such a way that someone with this deficiency can still disentangle them. So here it was, this is not what this is doing. So is the window size flexible? Yes, you can. So I didn't show this, but you can make it larger. This is currently a little bit awkward. You have to use your arrow keys to make it larger and smaller. I want to also make it so that you can just drag it in the future, but that's currently not implemented. Okay, so can you limit the number of grayscales? Yeah, no. So right now it's just standard grayscale in RGB, so like 256 different levels. Can this be used as a library? No, right now it's not. But I mean, there are libraries which do this. So if you want to do this, Color Spacious is a very good library for this sort of thing. All right, I think that was all the questions.
Yeah, thanks very much. So we could have a full overview. You managed to precise on time. Thanks very much again. So by all means, if there are any questions or chats about Monolens, just continue on Slack as ever, right? So our next speaker will talk about basically reporting a progress of a program to your mobile. So I think I'll have to see that one to understand. Because it could mean a lot. But Matthias, I see you there. So please start sharing and off you go, please.
Yes, hi. I am. Okay, now you can see.
Yeah, that should be okay.
Okay, yeah, so I will talk about reporting the progress of a program quickly and easy to a Telegram chat. So the motivation for this, I want to start. Suppose you are in the lab doing some task that is very stupid, repetitive. It's just a for loop. For example, this is something that I usually do. It's a two-dimensional scan with a laser, and this it's just a for loop that takes a very, very long time. It can take, for example, 1 week. So it would be nice in this case to have something that gives easily an estimation on when will this end. Also be able to check the progress in real time without having to go there and see how it is going on, and also get notified when this finishes. So for this, I developed a simple package that uses a Telegram bot to do this job. So this is the package, just a screenshot and also the link for those interested. So basically, how do we use it? There are one-time steps. So obviously, you have to install this package. It's very simple. And then you have to create a Telegram bot, which is also very simple, and there are a lot of tutorials around. Then on the regular usage, basically we have only just to insert 3 lines of code in our program. First, we have to import this package. Then we create one of these reporter objects. This is a single line. I just wrote it in this way to make it easier to read. And then inside our very long for loop, we just report each completion of the loop. So in this case, this reporter will send a message to some Telegram chat. When it enters into this with context, it will automatically estimate when it will finish. It will update the original message as the chat goes on with new information. It will send also a new message when it finishes. And what it will not, which is also very important, it will not raise any error. So it doesn't matter what happens. It will not make your program crash. It will not hang your program or make it slower. It will not spam your Telegram account with hundreds of chats. And it will not print anything in your terminal, so the terminal stays clean. And basically, this is some marketing, but you will get a release of having to go check there, and you can worry about more important things, and you will know when the program ends. So for this, let me just run an example. So I will bring my Telegram chat here. I hope you can see it, and I have also this Jupyter notebook, some general comments, but here, let me run this. I am just importing the package, and in this line, I am importing another package where I store the token of the bot, which is something that you must never do, make it public, and define some constants here. And then this block basically has the same code that I was showing in the example. So let me just run it, and you see here how it sends a message saying that it's starting this loop. Then as the progress goes on, it updates the same message. You can see here the progress, how is it going on. Let me show here, this is the structure of these messages. So you have an optional loop name, then you have some information, an estimation on when it will finish, the percentage, and information on this message. And when the loop finishes, it automatically tells you this, and it sends a new message which is linked to the original message. So this will create a notification in your Telegram account, so you know that it has finished. So let me show some more examples. So for example, suppose that there is some error. This is not due to this package, but due to some communication problem with the oscilloscope or whatever you have in the lab. So let's see how this works. The loop starts. Here I will manually raise this error. This represents some problem, and you see that in this case, it tells you that it has finished the program, so it went outside this with statement, but it did not reach the 100%. So in this case, you know that some problem has occurred in your program. And then also, this is not limited to just having, of course, a single loop. You can use the same bot to report as many loops as you can from different computers. So to make this example here, I will just use the multiprocessing package to run 3 of these at the same time. So we can see this function is just to wrap to be compatible with this package. But in this last cell here, I am running 3 of these 4 loops at the same time, and we can see that they are working as expected. So this brings me to the conclusions. This is it's a really very simple package, but it's really useful. I am using it almost all the time in the lab. That allows you to report not only from the lab, also data processing to a Telegram chat, so you instantly know what is going on. It's effortless because you just need 3 extra lines of code in your script. It's safe in the sense that it will not raise any error if you lost the connection to the internet in the lab. It just keeps waiting and displays a warning, but that's all. And it releases you to go there personally and check what is happening. You just receive the updates in your cell phone. And this I have used it in Windows, Linux, and also in a Raspberry Pi computer. So basically, this is all I had to share.
Very cool. Thank you. We've got a few questions on slide already. Do you want to share, or shall I do it for you?
Yes, let me see. I can
You prepared. Very good.
Let's see. Okay, I often wanted something like this. Send mail. I really, I don't know about this. Send emails. This package, it's very young. I just started a couple of months ago, and I wrote it to my needs. But for sure, all these other things can be added to get more functionality. So what is Telegram? Okay, Telegram is something like WhatsApp, but cooler. Basically, you can create bots that you can, there is a Python API, so you can control the bots through Python and of course other languages too, and send this kind of messages. It's played nice with. I don't know what's the meaning of this. I'm sorry if it is too obvious, but okay, maybe you can write me in the chat to clarify this. Another loop will be a while loop. Reporting the progress wouldn't work there. Just wrap with a for loop. If you want to report with a while loop, you can do it, but you have to know when this loop finishes. If it is a while loop that the cutoff condition is something inside the loop and the number of loops can be different each time you run the program, then you can report, but you will never know when it reaches the 100% of completion or not, basically. So that's the reason with while loops. So this one.
Last one, maybe.
Okay. Yes. Yes, in fact, a couple of hours ago, I finished one of these messages that was a 2D scan that has been running for 1 week. So it can take any time you want, basically. No, this is not only possible in the mobile. Here, for example, this is my computer. It just goes to your Telegram account. Okay, so that's it.
Sounds good. Yeah, thanks very much. I'm sure that you will have more questions offline. I can bet on that. That's very nice. It looks very cool. Thank you for that. So now we move on. Olivier, I think I have made a course as well. Should be ready. So yeah. You lightning talk around the CMD module. Let's go ahead.
Yeah. You see correct my slides?
Yeah.
Perfect. So thanks for the invitation. So here I'm going to discuss how to recreate the shell experience and follow basically what we have done actually in MadGraph. So while speaking about user interface, so from my point of view, that's one of the main crucial elements for any applications, even though a lot of people really don't care about it. I mean, the most important part, of course, of any applications is the physics. It's what the problem your code is able to solve, obviously. At the same time, the user interface is really the first thing that users are going to encounter. So they came to your program, of course, because they want to solve a given problem. But after, there are typically many solutions for a given problem, and they are going to use your program or not, depending on how fast they can go from learning your program to the solution to that problem, obviously. So it's important, to my point of view, that all user interface is intuitive. So even if people, most of them doesn't consider that as important, I think it's really important. And people are sometimes confused about themselves, because I hear the same people saying, I don't care about user interface, but then be extremely nitpicking about every details on them. So that's a bit confusing. For the developer, so as people developing, it's important that the user interface is quite flexible, obviously, so they can include new features. That's quite common in ING physics. You start by being able to fix a small problem, and then people come to you, oh, what about if you can fix this, and then this, and then this, and your program suddenly needs to go actually to basically fix all the problem physics. So my computer is frozen, looks like. Do you still hear me?
Yeah, I can hear you. The slide is still on page 2.
Yeah, me too, actually. It's frozen there.
No, nothing I can. And let's see if you can close it and reopen again. Or...
Yeah, it looks like I cannot do anything.
Wait a second. I can try and share it for you. I mean,
yeah, let me try to stop sharing my screen. Yes. Then maybe we try sharing the screen. Let's start that.
Oh, it's a very big file. Now I see. The PDF is 154 megabytes. Is that correct?
Yeah, I'm not. Yeah, maybe it's possible. I don't know. Yeah, do you see my screen now?
A second. Yeah.
Yeah. So let's try that, and then if it's froze again, maybe you can try to share your screen.
Yeah.
What I want to describe here today is not the full details of the user interface, but basically what we are using in MadGraph and the building tools we have used to build that inside MadGraph. Because I hear a lot of people saying, "Oh, your user interface is fantastic." There's a lot of good feedback. So I want just to basically say here, okay, that is we have done it. That's the main idea. Then so that other people can basically use and do whatever you want for your own code. So there are basically two types of command line interface. I'm interested in command line because that's basically what most of people are using, of course, in energy physics. And basically, you have by parameter, you can pass, you have a functions and a bunch of parameter. You know a lot of programs on that. Or you have interactive sessions. And there you have more, you're asking the user to interact with you to ask a lot of questions. And it can be really quite damping, I would say, because if you have a lot of branching, that can be quite a nightmare easily. Sometimes, of course, it's what you want. The function space, for example, that's exactly what you want. You have a lot of fine control on exactly what's going on. So that's exactly what you want. But then it's very difficult, of course, to script that part, obviously. So what I like about user interactive session is that it's much more user-friendly. You can really help the user to go to the solutions more quickly. The downside is if it's not coded carefully, it can be very difficult to script. And therefore, it's quite bad in the long term to maintain that, especially if you have a lot of questions, a lot of trees. So what I think is a good mix between the two is really a Python shell interface. So it's really an interface like shell, where you have auto-completions, you have a set of comments with different set of arguments, and you have auto-completion. That's really helps the user to go through. And one thing I like quite a lot that we have implemented is a tutorial mode. So the first thing you arrive on the shell, then you say to the user, if you don't know to use this code, type tutorial. And then the user can type tutorial. And then you have precise instructions how to go, and then basically make the code himself, make easily to go through for any Lambda user that for after 15 minutes, in our case, at least in our tutorial, 15 minutes, you can go and learn all the commands that are needed basically to run the code. So this is actually very simple to do. You have a Python built-in package for doing that, which is CMD. The downside is extremely basic. I will show you in 2 seconds what it's doing. It's extremely basic, very simple to handle. That's good, obviously. But then it doesn't have any advanced feature. So if you want that, I will not cover that, but you have CMD2 package, but that one is not built in. You need to install by pip, very easy, obviously. So here's an example of a CMD interface, so a shell interface with one command, the hello world. So not very long, very easy to do. You of course first have to import the CMD command, and then you instantiate a new class. And then you can go to functions. So the first one is mandatory. The second two others are not really needed. So the first one need to start by do underscore and then the name of your command. So that's really how the interface know, okay, that's a new command that the user can type. The user can type hello world, then anything you want. In this case, there's no parsing at this stage. And then you define the functions and what needs to be done in this case. So really that's just a keyword, do underscore, and then you can do whatever you want. Second functions is help, so that you can customize the help. The default is to use the docstring of the do underscore functions, but you can basically here even more extensive commands and basically build around that. And the third function is a bit difficult, I would say, to code. That's really what takes us a lot of time to do it correctly, I would say. But that's very useful, is this auto-completion feature. So that if the user type this, what should I do to extend the possibility? And therefore, the next thing to run is just basically running the code. It's depend on read line, and that makes sense because then you have history and all this auto-completions mode, obviously. One small trick is that In Mac, they have something slightly different. So in my case, I need to bind the completions like this and not like that for normal read line, GNU read line, I would say. But otherwise, that's very standard. And that's basically it. And that you have now a full workable interface, in this case, with one command, so not very useful. Let's give you a lot of freedom, that therefore to add new command, add a new mode to your program, and so on and so on. So let me go to the demonstration. So here on the right, I have the one of MadGraph, when you see the help command with many commands that's allowed to go to a lot of directions. And here on the left, I will just run the command I have set. So it enters me to a command interface. I able to completions, and it tells me that I have two commands that start by H actually to complete up to L. So I can do hello world. And then again go to completions. And that's it. So that really gives you a lot of freedoms to basically do a nice user interface where you can have interactions with the user, but at the same time, if all the freedom and power, power of basically single commands next to each other. You can combine them, of course, and stuff like that. So to finish, this basic feature of CMD, there is actually not much more to that. So that's very simple, but not that much powerful. So if you, in MadGraph, we've done it to basically add a couple of features to simplify your life at the end of the day, like better completions, we have a way to say, or what the user printed so that we have nice bug report and so on. A lot of that is already available in CMD, CMD2, sorry. Typically, we don't try to have that much dependency in MadGraph, so that's why we didn't rely on CMD2. Yeah, in CMD2, like argparse automatic, so you define your functions with argparse and automatically help and auto completions. That's wonderful actually to in MadGraph as well. Thank you.
Thanks very much. I don't. Okay, you're already sharing. Thanks very much. She does know, but so maybe I can ask a question. You just mentioned MadGraph, but how is this really making a difference, an impact for your daily work, actually? Well, that's really is also because in MadGraph we have, I would say, our main code, but we have also side project in a way. That's really on the basic of MadGraph, which is a matrix event generator. So that's the part which is basically common to everything. But then after that, you can say, oh, I want only to evaluate one matrix point, or I want to have that code, but in Fortran, or that code in C++, or I want to do a phase space integration. So I want to do a reverse engineering from going from the data to the theory. So in that way, we have really a lot of options that's starting the same way, but then diverge completely. And that's really the way in MadGraph it's done. It's typically always the same first command. Then depending on what you want to do, then you decide a new command actually. I see. By the way, are you a phenomenologist or an experimentalist? Well, I would say I'm an IT guy now, but I was a phenomenologist at the beginning. So if I see nothing else, then we continue. We actually we're pretty much essentially on time. Thanks very much again. So for anything, just continue offline, all right? All right. Next, we should have Christophe, also yes, from Université Louvain. Yeah. Yes, I'm there. So okay. So you can share in your 10 minutes. Yeah. Okay. So nominally 8 + 2 to last a little bit of time, but less likely flexible. It's fine. Okay, do you see the screen like this? Yeah. Okay, so in this talk, I would like to show how we used Python scripts in FreeCAD to help with the detector design at HL-LHC. I will start with some brief introduction about the project, and then I will go into the tool itself. I don't think I have to spend a lot of time here to describe the HL-LHC project, just to say that it will really push the technology to its limits with a tenfold increase in radiation doses. So as a consequence, the CMS collaboration is building an entirely new phase 2 tracker with an improved radiation handling, increased granularity, and reduced material budget.
So that project, the CMS tracker upgrade, is bringing together engineers and physicists to design, to optimize, to study, and to plan the new detector. We have several constraints from the existing infrastructure. We have to fit into the same detector using the same service channels. And at the same time, the resources that we have to be shared with operation of the current detector for run 3. So it's very challenging, and new tools are being developed for that purpose that have no equivalent in previous iterations. And speaking of tools for the optimization of the detector design, and also for planning the integration process. So the CMS tracker is depicted on this slide. Here you see 1/4 of the detector, and it's basically split in two parts. We have the inner tracker that is made of pixel modules, and the outer tracker with two types of modules. What we call the PS modules are detector elements with on one side silicon strip sensors, and on the other side micropixels. And on the outside we have two S modules with two sets of strip sensors. And for this work, it's all about the TED, the tracker end cap made of double discs. That is that part of the detector. So the fundamental mechanical structure for the TED is what we call a D, and you see a picture here. So it's made of composite material. Each D has a semicircular shape, and it provides the mechanical support and cooling for the detection modules that are put on it. And you see there the 2S and the PS modules. So 2 Ds form a disk, then 2 disks form a double disk, and you need 5 double disks to make a TED. And you have two types of these, what we call TED1 and TED2. They are slightly different because of their inner radius. What you see here is the TED1 for the two first double disks, and we have TED2 with a larger inner radius for the last 3 double disks. So that's the device we need to build. Now, in terms of services, each module is a standalone detector, and it is equipped with 3 wires and 2 optical fibers. We have a low voltage differential pair to power the module. Then we have an HV- line to bias the sensor, and we have an optical fiber pair for data readout and communication. The cooling is done through a two-phase CO2 cooling, operating at -35 degrees, that is embedded into the support structure. And all these services are routed first radially on the D to reach the periphery, and then from there longitudinally to the service channels at the end of the tracker volume. And you see there on the photograph how it looks like. The tracker will come in that central area there, inside the greenish calorimeter, and then you have these service channels that are on the periphery. And for the outer tracker, we have 6 service channels. Each of them is split in 3, and we have separate channels for power, optics, and cooling. And this service distribution completely breaks the symmetry of the tracker. And in the end, we have 8 D geometries that we have to consider separately. And you see, for example, for TED1 on the bottom plots, how the optical services are distributed in the different service channels, and how the power services are distributed. So we don't have to go into the details, but you see that it's a totally different routing. So this is an additional complexity. The standard tools in the community in CMS are those 3. First, we have to speak about layout optimization, and for that we have what we call TK layout. It's a modeling and performance analysis tools that has been developed at CMS for the study of the silicon tracker, and that can be used outside of it. It is essentially a command line tool that generates the geometry based on simple config files. And then the support structure are added, the services are added. So you have a realistic description of the tracker. And the output from that tool is a Geant4 geometry, web pages, CSV files, and so on. Then we have Geant4 embedded into CMSSW, the CMS analysis software, and it's used for physics performance studies. And it has been used, for example, to produce all the results for the technical design report and for the publications. And finally, when we speak about engineering design, we are usually using CATIA, a CAD software that is essentially an interactive tool with possibilities to script in Visual Basic, and where we will describe all the mechanical aspects and the integration with other sub-detectors and so on. What we are missing in this very specific project is something that combines interactivity, interoperability with the different other tools, with Geant4, with the TK layout, with the HEP ecosystem in general, and also something that has automation built in because of the many different geometries that we have to design and study. So we want to create several variations of the base model. We need to navigate and visualize the geometry and the logical organization. We're interested into the geometrical hierarchy, the unique ID of each module and so on, but also of the grouping by power, by optics, by cooling, by service channels, etc. We also want to study the service arrangement, combining mechanical and physical aspects, and potentially many more. So in that context, we tried and we wanted to investigate the use of FreeCAD. So FreeCAD is a general purpose parametric 3D CAD modeler developed completely open source with an GPL license. FreeCAD is aimed directly at mechanical engineering and product design, but it has also a wider range of uses. You can use it for architecture, for finite element analysis, for 3D printing, for CNC, and so on. Its main characteristics are that it is feature-based parametric modeler with a modular software architecture, and it's possible to provide additional functionalities without modifying the core system. What is interesting for us today is the following statement that appears on the website of the project that says that FreeCAD is built from scratch to be totally controlled by Python scripts. Almost all parts of FreeCAD, such as the interface, the scene content, and even the representation of this content in the 3D views, are accessible from the built-in Python interpreter or from your own scripts. As a result, FreeCAD is probably one of the most deeply customizable engineering applications available today, they say. So, for us, what were the design choices? First, we aim at an open tool for experts. So we decided to develop within FreeCAD to use its interface. The alternative would have been to use FreeCAD as a library with a custom user interface, more restricted, but here we really wanted something open. Then, since we were not sure about the capabilities, we wanted to go for incremental development with well-factorized units. So we went for using macros. Macros in FreeCAD are basically Python scripts that are executed within FreeCAD. There are alternatives, for example, to use what they call FreeCAD workspace, but then you have an additional overhead, especially at the beginning of the project. And also, we wanted to have access to the cabling information from within FreeCAD. So we decided to include all the relevant information in the model itself. So that's once created, the model is a standalone representation of all the information that is available. A disclaimer here is that I'm neither a FreeCAD expert. I discovered the tool like 1 year ago, and I'm not a full-time Python developer either. So you can take it as an adventure that took a few months. But this is part of the equation, and you will see that we can do already a lot in that context. So first, few words about the organization of the FreeCAD models. We have a relatively flat structure. So here you see a logical representation of one file. We first have the D mechanics. Then we have a set of hidden module templates that are used when we populate the geometry. And then we have one group per module. And within that group, you will find the geometrical representation of the module, cabling information, and that cabling information is an app feature Python object, basically a list of properties with their values. And this is how you see that in FreeCAD. You have a little table with the different entries and their values. And then you also have all the services that are attached to the module. You have both the 2D and the 3D representations that are visible there. So I will now go through a few use cases. I will show some Python code, mostly to show the API that is provided by FreeCAD, and then I have some screencasts. I decided to pre-record some examples so that I can speed up the replay to save a bit of time. But for the question time, if you want, I can do some live demo. So the first thing to create a model is to generate the support structure and then iteratively put all the modules, the PS and the 2S modules, using the coordinates and orientation from the TK layout. And the third step is then to add the logical cabling information using the app feature Python object. And you see here the code that is used to place one module on the mechanics. So you have a method to access the current document. Then you can add an object. We add a group. And in that group, we add a module. It can be a 2S or a PS, depending on the case. And we set the position and the placement. So the placement is basically the position and the orientation. And that's it. And you see the API is pretty straightforward. So then when you run this kind of scripts, this is how it goes in FreeCAD. We select we first create the mechanics, and we select the data file with all the coordinates, and here we populate on one side of the D. You see it's putting first the PS modules and then the 2S modules. What you can see is that we've created additional buttons in the interface, and each of these buttons are linked to a single script, a single FreeCAD macro. Okay, now we'll go to the other side of the D, surface 1, and again, we repeat the process. So yeah, the model is basically ready at this stage, and you can see on the side that the file is now populated with the mechanics and all the modules. And the last step that we'll do here is to set the color. We'll use color to encode some of the cabling information. So this is what we just saw. We can also use a color scheme to relate to some of the cabling information. And for that, we want to loop over all the modules, so we access them in the active documents based on the type and name. And then we access the cabling information, get some property, and use that to set the color. And setting the color is nothing more complicated than accessing the module, again by type and name, and set the shape color of the corresponding view object, and that's it. So the result for us is that for a given geometry, we can get different versions, different colors, and have a description of the optical group, of the optical service channels, of the power service channels, or of the test group for the integration tests. So it's really easy to inspect the logical cabling based on that. Third use case is about services. The model we have for the optical fibers and wires has been developed in LaTeX using the TKZ package for historical reasons. And what we have is for each of the D geometry in each of the side, we have a SVG object that contains all the different paths. So what we need to do is to import the path in FreeCAD, extrude them as 3D object for a more realistic visualization, and then we can do some in-depth analysis. So we can look at the length, at the curvature, check the routing, make sure that the model follows the various kinds of constraints that we have. And you see here, for example, two results that we obtained with Matplotlib in a later step. The first one shows the curvature along a given optical fiber. So what you see is the XY position on the DE, and color-coded, you have the curvature. Another result is about the length. So this is the length of the individual optical fibers. And just integrating, you can get the total length. That is something like 1 kilometer for one end cap. And of course, we can do much more from the model as soon as we have it. So how do we do the import? Again, I will not show the full code here, but you can see that well, there is a first step that is about getting all the fiber object and grouping them by name. And then we loop over these groups. For each group, we create a sketch, so a 2D object, just with the FreeCAD method. And then we have to specify a few options. We can add constraints. So the sketch that is obtained there is made of individual paths. Well, the constraint that we add there is that these paths are connected. So it will use the manual modification later on if we want to. And then there is we call another small method that is just putting that sketch in the group of a given module. So this is that's good and a bit more executed. So we load an SVG file. We have to specify on which side of the D we want to import the cabling. There is an automatic pop-up about the scale, and now FreeCAD is loading the SVG object. There it is. And now our script is looping over all these paths and is creating sketches that will then be put on the proper location on the D. This is a relatively fast process given the complexity of the task. And in a second, you will see all the services that have been imported on the model. And here you see a zoom on part of the surface where you have the various services, power and optics installed, and in that case also extruded in 3D on the surface. One last use case that I want to mention is about simulation of the assembly sequence. So once we have a full model, we want also to simulate how will be the work in the lab when we integrate the various models on the mechanics. So we have a sequence file that tells us which modules comes first, and we want to simulate that in FreeCAD. And I show that because scripts can also be used to add some user interface elements to FreeCAD. And in this case, we add a side panel, and all the callbacks for the different UI elements are functions defined in the macro. And the code for that is pretty standard if you know about Qt and about PySide. So it's we use in this case the UI loader. We load the file. That file has a description of the user interface. There is some configuration to be done. That's where we define the callbacks. And then to add it to the FreeCAD window, we just call this method to get a handle on the main window, and we added a widget. So it's pretty standard PySide code. does some very light FreeCAD additions. And yeah, here is a small demo. We execute the macro. This creates the side panel, and then we use it. We load the YAML description of the assembly sequence, and then we can go through. We'll see in this case we even select. We have another focus mode that will zoom on the component that is being processed. And you'll see here we put a module, we connect the power, we connect the optics, we move to the next module, we connect the power, we connect the optics, and we go on with the third module and with more. And at each step, you can see on the side panels that the object that has been processed is highlighted. You have all the information about its position, and you can easily access the corresponding cabling object from the CRUD. Here we go on without the autofocus mode. We can also go quickly to later steps, or here we go even to the other side. We'll go a bit further, and then there is also a mode where you can just automatically play the sequence from a given place. And here it goes all by itself. So it could be used to make a recording and have a small movie. Here, of course, it's a random sequence. We still have to decide on the exact assembly sequence, but this gives the idea. Okay, so it's already time for the conclusions. Just to say that the construction of the new CMS central tracker for HL-LHC brings new challenges because of the size of the project and the complexity of the detector. And using Python allowed us to make FreeCAD into a wonderful tool to manage the construction project. So we use everything that the use of Python in FreeCAD makes it very versatile and easy to interface with other tools. You can control most of the elements of the user interface. So we used it mainly to extend the application for our needs, but you can also do the reverse, and we have some projects for that. You can use FreeCAD as a library, as a Python library in your own project. I've not shown that, but there is an integrated Python console, and it's pretty useful because it displays the commands for each action in the user interface. And it's a great way to learn the API just by doing. You select a component, you change the color, and then you see what are the Python calls for that action. So all the tools that I've shown today were developed in less than a year without prior knowledge of FreeCAD. I think it corresponds roughly to 3 months' work, looking at the GitLab logs, and the full set of scripts are something like 2,000 lines of code. I think all this makes it a good candidate for any project that needs a 3D dynamic visualization of a CAD geometry interfaced with other components in the HEP ecosystem, be it Matplotlib, Root, Geant4, you name it. So I will stop here, and of course, welcome your questions.
Thanks very much. That was very interesting, a bit different from what many of us do as an analysis work, so to speak, but still interesting to see how you can solve it with Python. So you have a few questions there.
Yeah, okay, let's go through. So if FreeCAD is passing 3D visualization through customizable.python, is it using NumPy array for performance or for loops? I've not seen any use of NumPy in the FreeCAD code, in native code, but you can use it yourself. Yeah, there is no restriction on the kind of library that you will use in your project. Right now, FreeCAD is using Python 3, PySide 2, and you can load, you can import any package that would help for your project. Now, whether they could gain in their internals, I don't know. They're already using pretty advanced open source libraries for most of their work. They are using Open Cascade, for example, for the 3D part. So I hope it answers the question. So if you found limitation compared to other softwares for your own work, as I said, for the Python part, it's pretty open. I've not seen in any place a limitation in the kind of package you can import. So even if it's a macro, you can really consider that as a Python script. And if you want to do things, well, maybe one thing, if you develop your own Python library, it may be tricky to import it in a macro. If you want to do that, to build bigger projects, then it's probably better to start creating a workspace, and the Python code behind the workspace will then be a full Python module. And then you can develop just your module and do whatever you like. And then for the link with DD4HEP, I think it could be done. Yeah, I was thinking about that while preparing this talk. Here we just went straight from the description we had, because there is this sticky layout code that generates a CSV file with the coordinates and angle of all the components. And we already have CAD representation of the modules, the 2S and the PS modules. So we were just loading the step files, and from this 3D description, well, we basically copy paste the modules in the proper place. But we could certainly have a more generic development that takes DD4HEP or any other Geon4 geometry description and translate that into a FreeCAD model. Yeah, FreeCAD is basically built from basic volume. Well, the description of objects in FreeCAD is made of basic volumes. So you just have to describe using FreeCAD classes, or you build your scene. So if you have it already in some format, it's just a matter of writing the translation, some reader for in that case, DD4HEP, that creates the corresponding content in the scene. Yeah, I see no technical problem with that. It's a bit of work, probably.
Right. Okay, so perfectly on time. All right, so I think as usual, please continue. Please feel encouraged to continue offline. I know that people have been maybe a bit more shy than last year. I don't know why, but yeah, please continue offline if you're interested in any of these topics. Thank you again for your presentation. Thank you.
Welcome.
Oops, so I managed to mute myself. So we have the last presentation of the day. Andre, you should be co-host again.
Hi.
Yeah. All right. So you can start sharing if you want, and then.
Should I start my video too? I guess.
Not yet.
Oh no, yeah. Okay.
Yeah. Okay, not full screen, but we can see you.
Yeah, I'll switch to full screen, and
thanks.
If that's okay. So should I start?
Please, yeah.
Yeah. Okay. So just video. Okay. So yeah, so I'll be talking about a new package by the Muon Physics Object Group in CMS that we've developed over the past year or so to compute tag and probe efficiencies efficiently with Apache, Spark, and Parquet. So I'll spend a little bit of time motivating why this was sort of needed for us and talking a little bit about the technique of the tag and probe efficiency. But then I'll show like a short demo just to highlight sort of how easy and convenient it can be. So the idea is to hopefully inspire other groups, other experimental groups to also do something like that. So let me, so why efficiencies, right? So if you're in an experimental physics program, it's very likely that you, at some point in the analysis, you're gonna have to derive some efficiency. So whether it's like an object reconstruction efficiency or trigger efficiency, there are several different kinds of efficiencies that we need to compute as experimentalists. And at the same time, many aspects of the physics analysis that we do rely a lot on simulations, on Monte Carlo simulations. So it is really crucial to understand the limitations of our simulations and how and assess the validity of the simulations, because it's impossible to have your simulation to capture every single detector detail. That's just physically impossible. And there's always other physics activity that degrades the performance that you're not aware of beforehand. And so it's really important to measure the discrepancy between the efficiency that you measure in data and the efficiency that you simulate from your Monte Carlo simulation to obtain the correct representation of whatever physics you are studying. And so the way we do that a lot is by deriving the scale factors, which are essentially calibrations between the expected and the observed performance. So that's a really important part of any physics analysis. And so in CMS, in the muon-pog, a common way that we compute scale factors is via the tag and probe method, which I have a sketch here on the right. But let me just say that in CMS we mainly use the Z or the J sine resonances decay into 2 muons to compute the efficiency in data. So on the right here, you see a candidate event for Z boson decay into 2 muons. And I have in blue the tag muon and in red the probe muon or the probe track at this point. The idea of the tag and probe is that you can use the dimuon resonance, for example, Z here, to tag the muon with a very robust and very tight selection, and also ensure that the muon your sample of events corresponds to a dimuon resonance. And then you minimally select the probe, so you don't apply a lot of selection to your probe. And so your probe becomes your test bed, where you can check whatever selection you want and measure the efficiency in data by using as a leverage the tag muon. So that's the idea of the tag and probe. You ensure a robust tag and a robust event selection. You apply minimum pre-selections to your probe, and then you can use that probe to see if your selection passes whatever test you are trying to compute the efficiency for. So you can do that both in data and in simulation, and then you can compare the results. And that's how you can derive the scale factor. So that's one main role of the muon physics object group in CMS, is to provide these official scale factors and the efficiency recommendations for all the CMS analysis. And so it is quite a fastidious work, and it requires a really performant code because we have a lot of efficiencies to measure. So I'll show that a little bit. But this is just to motivate, right? So, oops, I think I went. Okay, so here I have a sketch of what a cut and count tag and probe computation consists of. So on the left here, you have your sample with your event content, which you then apply a very loose selection to store some flat end tuples. So this is what we call skimming. The idea of a very loose skimming is that you can reduce the size of your data set, but still make it reusable and flexible enough that you can compute all the efficiencies that you want. So once you have this end tuples, then you can apply a pre-selection to your tag, as I mentioned, like making sure that you have a very tight tag selection. Oh, I'm sorry, my mouse is going. So you apply a very tight selection to the tag. You apply a loose selection to your probe just to make sure that you have a Z event. And then you can use your probe and apply some denominator selection to it. And then your test selection, it becomes your numerator. So your test selection your probe may pass or may fail that test selection. So, and this is what we're measuring. We're asking, has this probe in this event that I know is a dimuon event, does this probe pass whatever efficiency, whatever selection you want? So what we do then is we bin this passing and failing probes in bins of the dimuon invariant mass. So here's a dimuon invariant mass, and you can see the Z peak. It's just a sketch, but you can see the Z peak in both cases. And so what you do is you cut and then you count the number of probes that there are within this window around the Z peak. And then your efficiency just becomes the number of passing probes over the sum of your pass and fail probes. So that's the simple example with the cut and count. You can also, instead of cut and count, you can fit the spectrum to a signal in the background shape that allows you to separate a little bit better the signal in the background. But I won't talk about that because the demo today is just the simple cut and count. But the idea is that then you can do this procedure, right? You start with your skim, You apply some selections, and then you measure if whether your probe passes the test selection or not. And you do that to both the data, to events in data here in orange, or the simulation of your events in simulation in purple. So you do this, you count the probes that pass and that fail the selection, and you get the efficiency in data, and you get the efficiency in the simulation. You can bin in whatever way you want to bin, and then out comes your two efficiencies, the efficiency in data and Monte Carlo, which you can then divide to get the scale factor. So that's the idea for the tag and probe. And again, this is a very general idea that serves many kinds of different purposes: trigger efficiencies, identification efficiencies, whatever you want to do. And just to emphasize this point, why we need such a robust performant code is because there are, in CMS, there are a lot of efficiencies to measure. So you can think of, they're all sort of factorized. And so to do an analysis, you need to measure your trigger efficiency. You need to, if you're using isolation requirements, you need to measure that. If you have, of course, you're going to have some identification criteria, and you need to measure that as well. So all of this creates a lot of possible combinations of efficiencies that you need to measure to keep track of. I won't go through all of those, but just to highlight that this is the official list of supported efficiencies by the Mu and Pog, and so there's more than 20 possible combinations. And then for each of these combinations, of course, you don't want to only measure the scale factor, you also want to measure the uncertainty on that. And for that, a lot of systematic variations are required to, on the number of bins, on the binning width, and so on. And in the end, it turns out that we need about, this is just a rough estimate, but about 10,000 fits to get all of the efficiencies. So that's a lot of computation. So this is why we need a really fast software. So over the past year, we have been developing just that package. It's called Spark TNP. And so we've been developed inside the Mu and Pog, but this was originally written by Devin Taylor. And the idea of this package is to leverage the CERN's Apache Spark cluster that's called Analytics to distribute this computation. And so we also use the columnar data format, which is Apache Parquet, that interfaces with the Spark cluster very efficiently. So by using these two tools, we managed to reduce the scale factor computation time from days before to minutes to an hour, depending on how busy the cluster is. But this is a really significant improvement for us. And we also made this framework available to CMS analyzers because oftentimes an analysis wants to create a new identification criteria that serves the physics model better. And so they can use the Spark TNP to compute the efficiencies for their own custom selection. And so we also training and continue training. We're doing training workshops for all the users and so on. So that's the idea, is to switch to this framework to compute the scale factors much quicker. So the goal today is to talk about the Spark TNP package and mention and highlight the convenience and the speed of the calculation, and hopefully make the framework or the technique available to the wider HEP community, because as I said, every experimental program needs to measure efficiency. So this could really be used outside. So here's the code base is now public in our Mu and Pog repository. If you want to check it out, I will highlight sort of the workflow of the software. So here you start with your CMS full event content. Then you run, as I mentioned, the skimmer, the interpolaser, to get your selection of tags and probes. These are the possible tags and probes that you have. You store those as flat root trees in EOS, and then you move them over to HDFS. HDFS is the Hadoop file system at CERN. So this is what Spark uses. Spark can access the HDFS, but it cannot access the EOS. So we have to transfer it to HDFS. Then we convert the root files to Parquet before plugging it into our actual Spark and TNP calculator. And I'll talk about why we spend time doing this conversion from root to Parquet, but it basically saves us a lot of time. And so once we have the Parquet, this is our input. And here we're doing this aggregator, which is flattening. We're calculating the probes that pass and fail whatever selection you want. And then after that, we can either fit the spectrum, as I mentioned, or do the cut and count. And then after that, we just plot the results and calculate the actual, scale factor files and efficiency plots and everything. And we make that available on the web page to the CMS analyzers. That's the overall framework. You can see that we use a Spark cluster to do the aggregation step. For the fitting step, we're still using Condor jobs. One goal of the package in the future is to also use Spark to do the fitting jobs. We think that's possible, but we haven't really tried that yet, but to completely drop the requirement on the Condor. But for now, we use Condor for the fitting jobs. So just to match the software to the physics, right? So again, the aggregator is doing that step where you start with the Parquet and tuples with your possible tag and probe pairs. Then you measure, then you look at which probes pass your selection and which probes fail. That you're flattening, that's an aggregator because you're creating a histogram out of all of the tag and probe pairs. Once you have this reduced information, then you can either fit or do the cut and count to estimate the efficiency. And then the results of that go into the plots that we want. So that's the idea. So as I said, we managed to really speed up tag and probe efficiency and scale factor computation. So I won't go into too much detail on the left side, but I just to highlight on the right side, with the previous framework we had, which was a pure root based and root fit based tag and probe, it would take about a night to calculate a single ID, a single identification criteria using one LX plus core. And by the end, now we are on this time scale of 1 hour to do all of our IDs, all of 20 plus combinations of efficiencies, and that uses using about 100 Spark cores. A huge speed up was using the converted Parquet files instead of running Spark on top of root files, which we used with this package called Laurelon. So from now, so this is quite a significant speed up. And so we wanted to advertise that because we think it can be useful to others. But the package itself has two user modes, which I call the script versus the notebook. So you can use the Jupyter notebooks in Swan, which is the service for web-based analysis offered by CERN, to do exploratory work. And that's what I'm going to show today, actually. But you can also do the official production using a command line interface. And that in this way, you just give it a configuration file that defines everything that you want the software to do, and it will do it, and will throw the results into a web page, and that's it. So it's really easy to use, and we've had a lot of success with users trying out the package and running their own custom identification efficiencies. So with that introduction, let's go to the demo. So I'm going to move over to the notebook. The scale of the stock interactivity is going to be in this 2 in the Pitvarsky scale. That's what I call in terms of interactivity. So I'm going to, unfortunately, we need CERN, Swan, and the Spark cluster access for this. So I think it's hard for just everyone to follow along. So I'll be showing you how to do, but please feel free. The code base is there, and you can feel free to play around too. So let's see. So let me just ask, can you see, can somebody tell me if you can read the font size?
It's a bit small, but it's readable.
How about now?
That's fine, yeah.
Okay, awesome. So this is the Swan interface, and it's just a Jupyter notebook, but it has a few enhanced features. And the idea is that the Swan service automatically interfaces with the analytics Spark cluster. So this is the really nice thing about this. So it will create a Spark object for you. You don't have to worry about it. So here's, I just restarted the notebook. There's nothing. So there's no Spark object, but now we're going to click on the star, and we're just going to connect to the Spark cluster, and we'll do that for you automatically, and it will create a Spark object that then we can use. So it will authenticate me, and so on. It's going to take a little while. So while it does that, I'm going to switch here to the config file and just show you an example of a configuration file that we're going to use. So the config file has all the information that you want the the efficiency, the tag and probe efficiency to run. So here, for example, I'm defining 3 efficiencies. So these are the numerator and the denominator. So loose ID, medium ID, or tight ID. And then you can do the pre-selection, as I mentioned. You apply a selection to the tag and to the dimuon pair, and you apply some minimum selection to the probe here. And all of those definitions are here. So everything that you use, you need to define. So medium ID is defined here, for example. And so those are the variables inside the end tuple. So basically, you define everything, you define your selection, you define your efficiency, and then you define the binning that you want. So you can have any kind of binning, PT, absolute value of eta, or the number of primary vertices, whatever. If the variable is inside the end tuple in the scheme, you can use that as a binning. And here, yeah, you were just giving it the variable, so when we say PT, we really mean the pro PT inside the end tuple. And then we can also give it a pretty name that will be printed. So that's all that the config needs. I mean, there's also some systematic variations that you can define, but I won't go into that here, just for sake of time. Okay, so going back to the notebook, we're now connected to analytics. You can see the green arrow. So if I run the Spark again, you see that it's in the memory now. So we can just use it. So I'm going to just import a few other libraries to show you. I have this nice trick for long-running computations. It's just a beep, it's just a sine wave, but you can put it at the end of your command and a long-running computation. So hopefully that was not too loud. I'm sorry if it was, but it will just alert us that the computation is done. So, okay, so now what I'm going to do is I'm going to import the Spark TNP libraries, and I'm going to import the configuration file that I just showed you. And with that, the first thing that we want to do is to load the Spark data frame and then do some pre-processing on it. So this is sort of one of the cores of the computation. So this is what we're going to do with the get data frame. We're basically going to load the Parquet files. Right, here's where we're telling Spark to read the Parquet files that we have. And then we are going to apply the definitions in the config file that I just showed you as additional columns in this data frame. And then once we have all the definitions, we can apply the pre-selection to the tags and to the event. And then we can do some other things like applying some weights and creating the binning structure that we want. And then in the end, you have the data frame bin in whatever binning structure you chose in your config file. So those are the main steps to get started. So I'm going to show you. So I'm going to just run that get data frame. And while I forgot to actually define it. But while it runs, so just to show this, what we're doing here, we're using half of 2018 data. So that's in CMS, that's run 2018D, but that's about 32 inverse femtobarns of data, which is quite a large data set. But in the end, after our skimming and tuples, we have about 7 million total tag probe pairs. So that's how many entries we're running in our data frame. And you see just how fast it is. Let me go. So it's loaded our data frame. So now we have the data frame. And just to show you, this is a Spark data frame, which is similar to a Pandas data frame, except that all the computations on the data frame happen on the Spark cluster. So you don't really have access to the data frame. It's just kind of the representation of the data frame because you need the Spark cluster to run computations on it. But just to show, but it has all the end tuple, all the variables in the end tuple were loaded into the data frame. Okay, so the first thing we can do, just really quick, is just to make sure that we have something reasonable. So that our tag and probe pair really does represent a Z boson. So here I'm plotting the pair, the dimuon invariant mass of the pair, of the tag and probe pair, and hopefully it will look reasonable. But you can see this is running in the cluster, And right now we're connected to 24 cores. That number varies a bit on depending on how busy it is. We can also look at the computation. And so the yellow is the number of cores that you have available, and the blue is the number of active tasks. So the goal is to maximize the blue as compared to the yellow, but that's not always possible. But in any case, this allows us to keep track of how our computation is proceeding. And so while it's running, let me just tell you about the next step, which is to get, if you remember the slides, is to actually get the pass and fail probes. So here, the next step is to take the data frame and to calculate how many of the probes pass your numerator selection or not. So first, we apply the denominator selection. Here, we require all of the data frame probes to pass the denominator. And then we do a group by operation on the data frame to bin and to calculate how many of the probes pass the numerator selection. So this is just, asking the question, how many of the probes that pass the denominator also pass the numerator? And that's going to be eventually our efficiency. Then you can see that we do a cut and count. We're basically just cutting on the mass bins to make sure that it's around the Z peak. And then we're recounting how many of events pass inside the mass window. That's basically it. And then we convert the results to Panda, to a Pandas data frame from a Spark data frame, and then we're done. So I think it's almost over here. Okay, so there we go. So you can see it just ran the computation on the Spark cluster. This just produced a plot of the diagonal invariant mass. This was about 2 minutes for 7 million events if you want. So it's really quite efficient in terms of processing time.
Andrea, just to say, there's 5 minutes left, including.
Okay, I'm almost done with the basic example.
Yes.
So now we're going to do the pass and fail, which we're going to calculate the efficiency, the number of probes that pass the tight ID over the number of probes that there are tracker muons. So this is going to give us the efficiency. Here I'm using as being the eta, the pseudo rapidity of the muon, but you can choose whatever binning you want, as I said. And so while it runs that, the last step then is to actually compute and plot the efficiency. So we have the probes that pass the tight ID, and we have the probes that fail the tight ID. And now all we do is take the data frame and group it in terms of the ones that pass and the ones that fail, and then we can just calculate the efficiency as pass over fail plus pass. Those are all the steps that are needed, and then we'll have a plot. So it's taking a little longer than usual. I think it's because the cluster is busy, but it's almost done. So I'll just do that one example and then I'll stop for questions, but you can do whatever binning you want. You can do multi-dimensional binning as well, and you can do it's pretty flexible. So this is the main point of the framework. For this notebook, you can do exploratory work. So we could go here and change the binning, change the IDs, and we can change whatever we want, and then just reload the configuration and then rerun. And you see, we have the plots in a few minutes when the cluster is not so slow. Sorry, it's a bit slow today. But maybe while it's finishing the computation, I can take some questions. Does that sound like?
Yeah, sure. Up to you, of course. There are a few questions on the slide, actually.
Okay. I think I'm seeing here at the.
You have the page, or?
Yeah, I have it open.
Okay.
So could you skip the root to Parquet conversion? Is running with 100 cores and root files via Laravel an option? What would the runtimes be? So we found that running with root files directly by using Laravel significantly slows down the computation. We're not sure why. I mean, this would we would need to take a deeper look, but it might be because of the caching that's done in Laravel. but we find that because you only need to do this conversion once, we find that it's much more efficient to just do the conversion the first time you produce the data sets, and then you just run on Parquet for all the other efficiencies. So that's usually the way that we, but it is an option. It's just slower. Oh, it's done. Let me just plot this. And there you go. We have the theta d efficiency as a function of pseudo rapidity, calculated from scratch in just a couple of minutes. So I usually get this to be 1 minute. So it's like 6 million events or so over 60 seconds. So that's about 60,000 events per second. So it's really quite fast. Just to show you why we developed so much effort into this package. But let me take another question then. Does the tag and probe process involve any iteration? Caching intermediate results for iteration was promoted as Spark's distinguishing feature over Hadoop originally. Yeah, so I believe it does do caching. But we haven't gone that far in terms of the optimization. But I think you're right, Jim, that we should be able to cache this. You're right that Spark does do caching. I don't know if you take advantage of it automatically. I don't think so. So I think this might be a good idea for getting even better performance for the intermediate results. Yeah. Okay. How can we access the Jupyter notebook about Apache, Spark, and Parquet? So the notebooks are in the code base. Here in this link, in the slide. And if you go to the notebooks folder, you can find it there. To take a look. You mentioned Laurelin, but are you using Python packages from the HEP ecosystem in your workflows? If not, is that because they simply aren't relevant? So I guess I'm not exactly sure which HEP ecosystem packages you're referring to. Maybe this is something that we can discuss on the Slack, because we do. I mean, yeah, I'm not sure which particular high energy physics packages you discuss. We just use PySpark and Matplotlib for now and NumPy. But this could be interesting if there's some packages that we can take advantage of. Okay, could you please explain the cut part again from cut and count name? I don't understand why we call it cut. Oh, you call it cut because you're cutting around the peak. So here you have you're binning your pass and fail histograms as a function of mu univariate mass, but you want to make sure that your events correspond to Z bosons. So you want to cut around the Z peak. That's what I mean by cut. So you can see the dashed line and the solid line on top of the dashed line. So out of all of the events here, we only use the ones that are inside this cut window. That's what I mean by cutting. Hope that can we use the Spark for jet efficiency calculation as well? I'm not sure what you mean by that, by Spark for jet efficiency calculation. Oh, sorry. Instead of muons, just jets. Yes, I believe you should be able to. I mean, if you can formulate the problem in a similar way of calculating passing probes and failing probes, then you can definitely do this. We have been studying. Now that we have this powerful framework, we can choose whatever binning we want, right? So we've been studying studying the efficiency of muons in the presence of one or more jets. So that's something that we're starting to look at. So for example, this is what this framework allows us to do. I mean, we could do that before, but the flexibility and the performance of this allows us to just, okay, ask the question, how does this efficiency vary as a function of jet multiplicity? Does it change? And so these are the kinds of questions that you can just, if you have that variable in the ntuple, then you can just go in here and add, n jets, and then bin, 0, 1, 2, for example. You could do that, and then you're done. You can redo the computation. So it's really versatile. And so, but to calculate the efficiency of jets themselves, there's probably a little more tweaking that needs to be done, but I don't see why it shouldn't be possible. Yeah. Sorry, I'm trying not to go over too much. I think, but I hope that I was able to give you at least a sense of how easy and fast it is to compute a tag and probe efficiency. Like I won't run the rest of the examples. I was just basically doing other binnings. But you know, in just a few minutes, we're able to start from a Parquet file and then just have the efficiency derived, which you can see here. So yeah. If there's any more questions.
Thanks very much. Yeah. So yeah, that concludes the day. Before everybody leaves, there's a couple of things to say. First of all, thank you very much for the speakers. I think there was a very nice mix of presentations, from tutorials to lightning talks and on a variety of topics. We'll continue tomorrow. We reconvene at the same time. But if you may have seen on the agenda, there's actually a social event starting half an hour before for those that are keen on it and available. And I'll let Ben give you more information about it. Otherwise, see you tomorrow at the same time. Thank you.
Thanks, Eduardo. Yeah, I'm just going to share my screen just to show this. Right, can you all see that okay?
Yep.
Brilliant. So yeah, so I mean, obviously PyHEP, we're all about trying to build a community and trying to connect all the different developers and the users and physicists and software engineers, and it's been really great to see the different contributions today, some of the lightning talks from compare, and then also, you know, Henry's tutorial and so on, and then also the questions coming in through Slido and the way everyone's introducing themselves on the introductions channel. So it's clear we've got a pretty great group of people joining in, and one of the things we would love to do, which is typically hard to do on an online event, is try and get people to meet each other properly. So what we are going to experiment with tomorrow is a new platform that I've had a hand in developing. It's called Remotely Green, and the point is to basically give us a chance to network, to get to know each other. So whether you've been developing a package for a long time, or whether you're someone who's just starting to use Python, this is a way for us to get to know each other a little bit, and meet new people, not just to connect with those that we already know. So we'll start this half an hour before the main session tomorrow. We have up to 100 slots, but we can increase that if it seems like we're going to need to. And all you have to do is go to the link that's linked from the agenda, and you'll be taken to this page. And that's it. Basically, if you arrive here tomorrow at the scheduled time at 1:30 European time, we will start the event probably just shortly after. And all you have to do is stay on this page, and you will be introduced to various other people using this platform. You can choose topics of interest. So you can see this list down here of the various topics that we've set up for this event. And I might tweet that before tomorrow. But you can, say, oh, I want to talk about tea and coffee, or I want to share some software horror stories. And so you can choose these different topics, and we'll put you together with people that have expressed a similar interest in them. And if before the event you want to test your camera, I won't do this now because I'm talking to you from Zoom, but you can check this before that. And that's it. We'll have a half hour. You'll have 5 chances to meet groups of people, up to 4 at a time. And each interaction will last 5 minutes, and then the system will shuffle you around to meet new people. So please join us, because I think it'd be great to get to know you all better. And it'd be interesting to hear feedback as well, whether people appreciate this as something for future PyHEPs. Yeah, that was it. Thank you.
Thanks a lot, Ben. Just a quick question in terms of login. Are there any special requirements, or it's very just straightforward?
That's a really good point. Thanks. So if I log out, I can quickly show you. It's pretty easy to do. If you don't have an account already, which I guess is quite likely, either you can sign in, you can sign up using a LinkedIn, or you can just put your own email address and a simple username and create a password. And if you do it the email route, just double check for a verification email. But that's a really good point. Yeah, you will need to make an account. This is for sort of legal reasons that we need to keep track of who's taking part. Yeah, thanks, Eduardo.
Well, thank you. Thank you for setting all this up. Yeah, so we look forward to seeing many of you joining online tomorrow, and Have a good evening or a good night for a few of you. See you tomorrow. Bye-bye.